So Arghya Kusum Das is our almost, he is like our students and our very near personality. So he has bridged between these two, IBM with our other institutions, because I am finding there the participation from other institutions like from IIT Kharagpur, Calcutta University, then is the IIEST, and from some basic science college also there is the participant. So I will request Arghya Kusum Das to say a few words about all these.
Good morning, everybody. So, thanks, Dr. Taki, for giving me the opportunity to talk here. So, first of all, as a coordinator of this first ever OpenPOWER workshop in Kolkata, I'd like to invite you all in the workshop. So, enjoy the entire day, as it is a full day event, and learn all the IBM related technologies, big data related technologies, genomics, AI related technologies, and all these things. So well, and let me introduce myself. So Dr. Taki already introduced me well. So okay, so I did my undergraduate from College of Engineering and Management Kolkata, which is college under W. Butt, West Bengal University of Technology at that time. Now it is McLeod years. And then I worked for Wipro Technologies for 2 years, and I did a junior research fellowship for IIEST. And after that, I went to do my PhD study in Louisiana State University in USA. And after doing my PhD study, I have joined as an assistant professor in University of Wisconsin-Platteville. So currently I'm working as an assistant professor there. So my research area broadly covers the big data analytics, and to be a bit more specific, many of my research are focused on big data genome analytics. So in the last few years, there are severe changes in technology, and as the changes are taking the world, the genome sequencing machines have started producing lots of data. And with those data, we are trying to answer some of the fundamental questions of the human life. Well, so those data are producing lots of challenges in the supercomputer. So in my talk later, I will discuss all about this. And regarding my collaboration or regarding my relation with IBM, I have the relation with IBM from my PhD days, when I got my exposure to Power 8 system at that time. So I'll share those experience after when I will get a chance. So well, that's about me in a nutshell. And well, regarding my consultancy experience, I am giving some HPC solution consultancy to many of the US institutes. As Dr. Taki told, I have some collaboration with Georgia Tech, some other universities, and some of the national laboratories like Argonne Lab. And then also I have some collaboration with San Diego Supercomputing Center and other supercomputing centers. And right now I'm trying to collaborate with Oak Ridge National Laboratory, where I'm expecting to get access to the world's fastest supercomputer summit, which is powered by IBM. So all right, so I won't take much time, so that's about me in a nutshell. So, well, enjoy the conference, enjoy the day, meet your thirst for knowledge, ask lots of questions, so enjoy it. Thank you.
Thank you, sir. Thank you all. Now, I will tell about a brief profile of Dr. Sanat Kumar Saha. Dr. Sanat Kumar Saha is currently working as Honorable Member or Eminent Scientist with West Bengal State Council of Higher Education, Government of West Bengal. So, now I will request Dr. G.S. Taki sir to come and tell about Dr. Sanat Kumar Shah.
Dr. Saha actually he is a, I should say, not only from the academics but also from several undertaking, government undertaking, industrial institutions also. So there he worked a lot on the particularly power systems, and he is related with the Department of Higher Education as already well mentioned. So he is helping the government in several ways, solving several problems in the arena of electricity, then is the environment and many more things.
Good morning to all of you. Dignitaries on the dais, of the dais, and my dear students. Particularly students, I call beloved students. I give them a lot of priority whenever I get an opportunity to speak out in any conferences, any workshops, any seminars, because we feel proud that India is having 1.35 billion of people in a huge geographical area. And out of this total population, 40% population that comes into the age group of 25 to 35. That's our younger generation. That's the students' community. They are the future architect of this great planet. So you are the founder stone for how you make this planet more a beautiful one to live together. Thank you, Professor Taki, for giving me this opportunity to be here this morning. I am not a computer man, I am not a supercomputer man. My specialization have been natural resources management, energy and environment, which is a global topic, the burning topic of today. We need energy security because Intel, IBM, HP, nobody will be in a position to work without energy. What is that energy? We have multiple sources of energy. Even this cube light working here, even I am speaking on a mic, even I am in front of the laptop. Can you imagine if we don't have electricity connection for a minute? Our total program will come to zero level. That's the importance of energy. India is the fourth largest consumer of energy in the world. First is US, second is China, third is Japan, and fourth is India. And India is the seventh producer of energy in the world. The per capita energy consumption of India is 624 kgoe as compared to the world average of 1900 kgoe. So that way we feel a bit bad that our energy consumption is so 1/3 of global average. Maybe due to less industrialization and the population. It's not, we should not take it in a negative mode. So our present government priority to have energy security, and by 2022, all the rural villages must have electricity connection. That's the mandate. And to have energy security, we have to have multiple sources of energy, giving priority to renewable sources of energy like solar, wind, biomass, hydro, and so on. On the other hand, we know, this is a very common thing, we must know and we must be knowing, that per capita energy consumption of any country that speaks about how economically, how industrially, and otherwise the country is developed. That's the status. As I said, although our energy consumption is less, it's not that we are not being rated to be a developed country sooner. We have to be very much optimistic for that. On the other hand, the recent publication of ICMR that speaks out that 1 out of 8 unnatural deaths in India is taking place due to pollution related problem, particularly air pollution, with particular emphasis on traffic pollution. And if we don't look at to environmental protection, so maybe in 10 years from today, we'll land up to a situation when 2 out of 8 unnatural deaths in India will happen due to air pollution related diseases. That's a big warning bell for all of us, you the young generation here, because we have to go a long way. We are senior citizens, we have few years left to live in this beautiful world, but you have to go along with your family a long way from today. So this is about the significance and importance of energy and environment, where I have been very much passionate, and I have been delivering guest lecture all over the world, and in the last 1.5 years I had been to Russia, I had been to Germany, I had been to China, I had been to Bangladesh, and I have too many countries to visit it very shortly. And my journey begins from school to almost all universities, national institutes, private MNCs, and whatnot. This is little bit, I thought I must take that advantage, although it is out of the place on which we are here on this particular, focus of the workshop. So, this is what I must tell some of the things which is there in my core of heart to share with you. When the student is ready, the teacher appears. What is happening today? I have been a student all my life, and today more so as we delve deeper into the world of machine learning and artificial intelligence. While such technology forces will define much of our future, we need to understand well that we need to look at them from the lens of advancement and not insecurities. I had an opportunity to talk to Professor Arghya a few minutes back to share with him the concern with general students and people. They feel artificial intelligence will take away their jobs, they are feeling very much insecure. And how nicely Professor Arghya has explained to me that it's not the warning bell, it is rather opening up new job opportunities for the young students like all of you here. I appreciate Professor Arghya for that. They are going to coexist with our natural human abilities that will evolve jobs and not replace them. What is it? The times we stop learning, we will get a feeling that we are being replaced by machines. What I already shared with all of you. The key is to learn to become a better learner. Understand our basics better than anyone else in the room. Understanding concepts of empathy, design thinking, algorithm, human experiences are going to be the fundamentals of our life. I am very sure Professor Taki gave me 5 minutes time and I have exceeded my time limit. My apology for that, Professor Taki. I wish and pray this particular workshop a grand success, and I express my gratitude to IIM authorities and Professor Taki, IBM, and all of you, my seniors over here from different universities, institutes, for giving me this opportunity to stand in front of you and express my little bit of share of experience of life. Thank you. Thank you. Thank you.
I just wanted to give you a brief background of how this workshop evolved. 3 months back, I got an introduction to the Professor Arghya, who is here in US. When I was in US, one of my colleagues introduced me to Professor Arghya over the email, and then we got connected, and we have been talking about how we can spread this, the OpenPOWER and AI and all these, the ecosystem worldwide. And it happened to be like he is also in India right now, and I'm also in India, and we just synced, and we wanted to have a workshop in Kolkata, and this happened here. Otherwise, it wouldn't have happened. I won't be here, and probably you may not be seeing, the power of the world, today's power of the world. That is OpenPOWER and the power. And the AI workshop, whatever we are talking about, this we have been doing it for last 6 years, many countries and many places. I'm going to walk you through on that. This is a great opportunity for you all to just listen to what we are doing today, and also a follow-up we can make. There are lots of resources available on the web and also in our repository, where you can go and take a look, and also you can engage with us on a project and other stuff. So feel free. This is a great opportunity for all of you over here. They are going to learn certainly something today and take it to your school going forward, and maybe exchange with your students. And you may get an opportunity to present also, like what we are doing today. One of the students is going to be part of this, presenting this too, like whatever we have done in the past. So, how many of you know already AI, machine learning, deep learning in this crowd? The students? Okay, cool. That's good. That's a good number. So then you can certainly help me out also, where we are going, and how you want to do it, and or anything, any suggestion, we will definitely integrate as part of the workshop too. So before, I just want to give you a background for today's workshop. I'm going to give an intro talk and also give you some background about OpenPOWER AI and what are all happening around the world, and what are all the resources available, and how you can get involved in this ecosystem. And then I will invite Professor Arghya to give you a background about, already he mentioned about the world fastest supercomputer, Oak Ridge National Lab and all. but he will also talk about his experiences on some of the applications, especially in genomics and other areas. And then I have Dr. Jayakumar, who is I would say technologist. He is a PhD from IIT Bombay, where we do have OpenPOWER Center of Excellence running there, and he's going to be spending a lot of time and also sharing his experiences on OpenPOWER AI and the other one, which is actually kind of evolving today, called edge computing. How many of you know edge computing? See, this is a great opportunity for you to learn about edge computing. Next 5 years, the edge computing is an opportunity for you, and there are lots of innovations there, on the edge computing, and definitely, you will learn about it, and you can start thinking about how you can create a small device attached to a bigger device or a bigger system and all. So that also you will be learning today as part of the exercise. And we do have some lot of work going on around edge computing worldwide in IBM's research, as well as the OpenPOWER partners and all those people developing solutions around the world for the edge computing. Edge computing and AI are going to be working together in the next 5 years. Believe me or not, there are a lot of opportunities also, you're going to get it. So all these things you're going to be learning today, and end of today you are welcome to come back and tell us what you want, or what is the future plan and other stuff. We will certainly help you out. I'm actually kind of a collaborator worldwide, and there are lots of engagements I do with universities and research labs worldwide, and you can look up in my LinkedIn profile. There are a lot of events I would have demonstrated through the LinkedIn, and also I'm running a the virtual university through YouTube, where I do record all of my sessions and then put it in the YouTube channel, where people can get benefited also in that. So with this, I want to just start my part of presentation: OpenPOWER Foundation and ecosystem, and also the talk about what is that and how it got evolved and other stuff. So in year 2013, we all wanted the architecture innovation. See here, most of the time in the last 30 years, where the power, Professor Taki, did mention about the Power 1 and other stuff, right? 30 years back, we were doing research on developing a new architecture innovation on a RISC-based processor, and that's how the Power 1 evolved, and then Power 2, Power 3. As we speak now, today we are at the Power 9 kind of the version of the processor platform. I would say here the CPU is the Power is also one of the CPUs. It's not one of the CPUs 20 years, 30 years back. Later on, Intel and other CPUs evolved based on CISC based and other stuff. So see the OpenPOWER, the need of OpenPOWER is basically is till I would say 2010 and all, we were CPU centric, and everyone was depending on CPU. Without CPU, I mean with CPU only a system can power up and can do all the jobs. And as the year went on, people realized that it's not just CPU, the system's capability, the entire system. See, for example, in our body, can we say that art is only the important component? I don't think so. There are a lot of other components also very important, right? Similarly, other components also very important. Similarly, on a system, there are other components also very important, like memory and the I/O, the input output storage, and the network I/O, the interconnect, and many things are part of the entire the systems capability. The entire thing will provide systems capability. That's what I'm talking about, the computer system. So we as a team like IBM put together kind of a plan to take forward this OpenPOWER idea to Google, Mellanox, NVIDIA, and Tian. How many of you know Google? I know some people are here. So the Google, So you guys recently participated in Google competition?
No, it's not a competition. We actually build an actions on Google.
Or some kind of components in Google?
Project.
Oh, project in Google, okay. Like similar, yeah, so okay, good. Good that you are here. And Google is one of our, the key partner in OpenPOWER. And Google runs on, some of the Google data center run on OpenPOWER systems. And just I want to tell you that, that's why, the 5 key members, initially wanted to have a architecture innovation. That means a lot of systems capability, they wanted to bring, not just a CPU centric. And one of them is GPU. How many of you know GPU system, the GPU company? Who is the number 1 GPU company today? NVIDIA, right. So NVIDIA is one of the, core partner, as part of the foundation. And Mellanox. How many of you know Mellanox? I know, definitely you may not know, but it's based, yeah, so people are here, faculty, but I'm targeting the students here. So the Mellanox is actually an interconnect company. What do you mean by interconnect?
Connecting devices across cloud platforms?
Not for platform, any platform connecting devices, any systems. Like it's basically connecting two computers. For that, you need a switch and a cable, right? The Mellanox provides that. That's an open source based, thing. And the Mellanox, the first one, to come out with, the open source based, the device to do that. And now they have been acquired by the NVIDIA. So NVIDIA and Mellanox are together right now. That is going to be shortly announced to, the final thing, going on. They already announced that, they are going to take over the company. So interconnect is also very important. Networking, then only, you can have a clustered components, right? You can't do everything in one single computer. If you want to join, like for example, a group can do a lot of things then, a single person, right? It's like that. So you need group of computers to, get your job done. And that time, the Mellanox coming to picture, and also there's an open model, is available. And, using that, they have become very popular because they built lots of supercomputers using that. Especially, the AI kind of, the supercomputers are all built using Mellanox interconnect, the switch as well as the Mellanox adapters. Got it? So these are the 5 companies, and Tian is another company, who builds, the system together. See here, they initially the first open core system built by Tian in 2014, and Tian is based out of Taiwan, and they got the chip from IBM, and they got the accelerator from NVIDIA and interconnect from Mellanox, and put together a kind of a platform for people to go and run their application and other stuff. That was the first system that Tian put together, and that's how the OpenPOWER evolved. So I don't need to read out all these, but there are
interconnect inside the chip that is done by IBM or that is done by the
no. You see there are
inside the chip.
Yeah,
This is external interconnect.
Yeah, it's an external interconnect.
This is an external interconnect.
Yes, sir. Because see, we don't want to have everything CPU centric. That's why we wanted everything the external. That's why the full systems capability you can get, and that's the idea of this OpenPOWER, and also we open source the complete our the platform called the motherboard. There is you don't see any server motherboard available where you can take a look and you can develop your own motherboard, but in our case you can do that. And I'm going to walk you through what are all the things we can do with the OpenPOWER platform. And definitely IBM also built using this OpenPOWER technology a powerful system. That also I'm going to walk you through. So we started in 2013 with the 5 members. Currently we have 345 members as part of this innovation, and that's the beauty of the powerful ecosystem we have. And so far 6 years right now, and we have been growing strongly, and there are a lot of partners coming in and developing products from chip to application. That also I'm going to walk you through. And this is a slide deck where I do mention about some of the partners who are involved from chip to the application. Have you heard about this kind of thing, like having a chip, like a server chip? I'm not talking about small, the toy x86 chip, which is available locally and all. I'm talking about real server chip. You can have a chip here. Chip companies are here, and then the board. The board is nothing but the motherboard. See here, the thing is there. It's not. I'm not talking about you get into hardware, but you should really need to build those skills for you to develop some innovations and all. And that's the main reason I'm here to talk about that also. So the board, and then the I/O storage, acceleration, and system integration, and software and implementation, HPC research. All these, the entire stack put together, a complete systems capability, and that's what you need to understand completely. It's not just running a .NET application on the top. Sir, I learned the .NET and I'm certified in .NET. Can I get a job? You may be able to get a job in the marketplace, but are you going to grow with that? Are you going to be really developing some innovation in that? I'm not sure about that. But in this area, if you spend some time on this while you are a student, you can do some magics here, some innovations here. And that's what I want to just convey to you as part of this the workshop too. So many things you can collaborate here, and you can encourage your fellow students also to form a group and start working on some kind of ideas. And that's the advantage of this open power and the complete stack availability, and there are a lot of partners involved and all.
Is there any Indian company in this list?
Yes, of course, sir. The Indian companies, in the sense, we mainly on the research. I mean the HPC research, right? There are a lot of colleges are part of that. Even CDAC is part of that. IIT Bombay is part of that, and many institutes. Even IIT Kharagpur is part of that. I've been working with IIT Kharagpur also locally here. And many
IISc Bangalore?
Yes, sir. IISc Bangalore. There are two teams: Balki's team as well as Govindarajan's team. They're all involved in this. So there are, see, I'm actually, the unique person, where I get connected with a lot of people, and collaborate on that too. And even shortly, probably, like Wisconsin also will be part of this, right? Yeah. So the beauty of, the collaboration, is actually basically to help you out to, get the knowledge. The knowledge is very important here, just not learning something small and, getting a job. It's basically you got to have a foundation, and the technology foundation, and everything is here in this stack, and we can also help you out, learn to teach you about the boarding, the boards, how to develop the new motherboards for the computer, server boards for the computer, and all the stuff. Even the chip level skills also, if you want to develop. Electronic students, probably there is an opportunity. Electrical students, opportunities to get out of this. It's not just the computer science students only, and also the mechanical student also. I've got a lot of opportunities. I was talking to your principal about that, and the automobile industry, mechanical. Many things are going on there. ADAS library, the autonomous vehicle, everything. If you want to have some knowledge on that, we do have a repository of things where you can get involved into, like the world, the super duper cars and all, like the BMW, Mercedes-Benz are all engaged with us, and even GM, Ford, all these companies collaborating with us on our platform. I do have details on that. If you want to know more about it, I can give you that too. So this is an important slide deck. You should remember always, when you want to learn about something, you have to go from the foundation and then application, so that you know what you are doing. And sir talked about overall the members, but academia members in India, I got nearly 35 members out of now it has grown to 150 in that. But there are other institutes also members in this foundation, especially a lot of people crazy about Berkeley, Stanford and all. They are all part of this. Berkeley, Stanford, BT, Virginia Tech, and University of Oregon, Oregon State University, Ohio State University. I can say many universities because I do collaborate directly with them. And it's not just in US, but in Europe also there are universities as well as research lab. How many of you know research labs in US and Okay, anyway, let me come back to India. How many of you know any research lab in India? Research and development labs.
Center for Development of Advanced.
Very good. You can call it CDAC, right? You are from?
I'm not. I'm on the camera.
Where do you work?
Cameraman.
Oh, cameraman. Wow. That's interesting. See, the skills are evolving here. Okay. So CDAC. You guys know CDAC, right? You should know CDAC. See, we have to be proud to say that CDAC is building a, the national supercomputer. They already closed down, the phase 1 with, Intel, Atos, and there's another company also involved. I forgot, but there are 3 companies, put together, putting together the platform for, the supercomputer in India.
You make something called forum server or something like that?
Yes, sir. That is actually in the past, but right now, as part of National Supercomputing Mission, they already awarded a supercomputer to build, and that is actually Atos from France, and Sanmina, one of the manufacturing company in Chennai, based out of San Jose, the headquarters, and Intel. These 3 companies, putting together the first national supercomputer. And that is going to be deployed. One of them is deployed in IIT Kharagpur. So, and now they are opening up the RFP for the second supercomputer, and we are also bidding for that. It's a bid. It's not just you go and choose it or something like that. Basically, they look at price, performance, and the long-term activities and all this stuff. So I just CDAC is one of the partners here, and they are collaborating with us.
CDAC has a campus here.
Yes, sir.
Chapter 5.
Yeah, I'm aware of that. I do work with the CDAC Pune, Mr. Hemant. He's the MD of CDAC currently, and also Sanjay and BCV Rao. These are all prominent researchers, and they do have very good skills in HPC as well as AI currently. And similarly, CDAC, we have labs in Europe and as well as in the US. Just for your knowledge, there is one lab called Oak Ridge National Lab. Professor Arghya already mentioned about it. And also Lawrence Livermore Lab, based out of California, Silicon Valley of the world. And these 2 labs recently deployed, 2 supercomputers. The number 1 and number 2 AI and HPC supercomputers. One is called Summit, the number 1 supercomputer, and the second one is called Sierra. And these 2 labs doing lots of research and development on top of the supercomputer. I'll go through that later. And Oak Ridge and Lawrence both are part of this, the academia and research partnership. And they have been collaborating with me and with this, the community for the last 5 years. So this has been extending a lot also. Any questions so far?
IBM has company over here. They have software companies. Are they not thinking in terms of this, whatever we are saying?
See, IBM has got mainly 4 branches. One is IBM Research, other one is IBM Systems, the third one is IBM Software, and fourth one is the IBM Services. And IBM Services is in Calcutta, and I'm not sure they are going to get involved in the systems kind of powerful things and all like. But there may be some teams involved, but I will come back to you with that later. And so these are the colleges and universities and research labs working with us closely, and let me know if you need any information on that. And then keep things in open power. So there are several things my colleague, I asked one of my colleagues to put together what are the things we can do in open power. So these are all more like system specific. No, you can immediately ask me, sir, can we do Edge? Can we do AI? Can we do HPC? Yes, on top of that, everything you can do. What is this? The first one, licenses the power processor, PowerLine and Powerline. What does that mean? You will get a license. There is a liberal payment, you need to make, to get the license. And you can get the license and you can start working on, the server class, new server class also, like another power processor too. that kind of openness we have here. And then the reference designs, Zeiss and Romlos listed are available for free. Can arrange an agreement for IBM to provide the free consultation service to OpenPOWER member to support on development. That means what? So the Zeiss is actually a collaboration between Google and Facebook and came out with a new motherboard. That is what is deployed in Google data centers and using this OpenPOWER technology. And Romulus is another one for the desktop as well as the workstation kind of the server-based systems. And we do have 2 systems available in India right now. We want to make it bigger also with your help. Maybe you guys can spread the word in Calcutta to get that kind of board and try it out. And there is the third one is the CAPI. So how many of you know PCI and all? PCI, the card, PCI 3, PCI 4. No, computer students are not there here. No computer students, computers and students. Okay, the PCI is basically a PCI card is to basically attach the external device to your motherboard so that you can do some kind of the network processing or a storage processing and all. And PCI is a traditional stuff. It has been there for several years, and now we added a feature called CAPI, Coherent Accelerator Processor Interface. Instead of PCI, you can have our CAPI card that integrates even the FPGA and other stuff to make your storage I/O as well as the network I/O faster. And that's the beauty of the innovation which we made working with few partners like Mellanox as well as Xilinx. And these cards are available through our partners. And if you have that, you will have more systems performance. Through all your I/O will get accelerated. That's the advantage of the CAPI one, and that is also part of this OpenPOWER innovation. And then the fourth one is the kernel enablement and support of power systems. So this one you can take a look at the kernel and you can make a modification also, like a cool thing, right? You are developing your own like that. There are lots of my colleagues in China. They do take out and even they started a company also with that operating system, and they will provide some support to that too. And the kernel also you can learn about it using that link. And then the firmware. The firmware is very important for your motherboard for providing additional capabilities and all. Motherboard means the system's board. So the firmware is not open in x86 based system, Intel or AMD or anything else. But in our side, the firmware is open. Open means you can take a look at the firmware and you can make some modification in the firmware to add some components as part of the motherboard, and then upload the new firmware to the motherboard. Then it will be your own firmware too. That is also possible in the OpenPOWER. And I think looks like for you it's like a kind of a Greek word or a French word, but you got to learn things, some of the things. These are the skills very important for India right now. Otherwise the innovation is not going to come here. Got it? Okay, so these are the 4 things. The 5 things. If you are able to get some ideas and skills, then the 3rd, 4th, 6th one, you can have your own system. You can make in India kind of system. That's what I want to tell you, that make in India. You can develop your own system here and develop India system. Then we can reduce our import and do export. That's how the Indian economy can grow. If you import everything, it's not going to grow at all. So these 6 things, if you do it, when I talk, I mentioned about edge computing and AI, right? That is easy for you to do also. Dr. Jayakumar will be explaining more details on that. How one can develop the edge device and take it to the entire world too. So many places the edge can be used, applying AI to the edge so that the intelligence will grow, and adding more capabilities to do more activities as part of the computing here. So that is also you can develop with all these, small skills, very important for you to, build the entire systems or edge or, any kind of, capable machines.
Intel is not there in this ecosystem.
Not there, sir. Intel is our competitor, I would say.
So in that case, is it really open?
Yes. Ours is really open, but Intel doesn't want to contribute to us, for sure. And now, Intel is getting beaten up in many areas because of this. You know, right? Intel just sold their mobile division to Apple. So Intel is not going to be in mobile anymore.
So in the sixth point, you said that you can build up your own.
Yes.
Most of the people will be having their Intel, the hardware. So
now they can have an open power hardware and build it on their own. And that's why we got two systems here to do that show and tell kind of thing.
So what is that?
We got two systems in India too right now. We do have, but I couldn't bring it here. But we can show and tell people also on that. Mr. Jayakumar will talk about that. He's building one of them. Yeah. So that's what, the skills are not there here. It's not that, the assembly only. We are talking about server class systems. These servers have been running in Citibank or ICICI Bank or Indian Bank in India. All these banks running these servers. Even IDRBT in Hyderabad, the Institute of, the Reserve Bank Consortium, they basically work with us a lot on that. So opportunities are, if you learn about it, you will get a lot of opportunities. And the future is all going to be very competitive. You got to know things, fundamentally. Then only, you can win in the marketplace. Right? And the other things, these are all, you can go through it. And, and also I encourage you all to have GitHub kind of, the repository. How many of you have GitHub here? Oh, cool. Cool. So you please, the rest of the people also, start looking at, what is GitHub and what kind of thing, you can get involved and, you can contribute and also you can create and, participate in that too. Even in our OpenPOWER GitHub also you can participate right now. Okay? So we mentioned, I mentioned, and also like Professor Arghya mentioned about the world's largest supercomputer summit. So the summit supercomputer, it is actually powered by IBM Powerline Processor with NVIDIA and Mellanox, and powerfully it is running and it is giving 200 petaflop of capabilities. Your application can take lots of advantage on it. It's a Summit supercomputer. It's built by Oak Ridge National Lab, based out of Tennessee in US, one of the states in US. Knoxville is a city where it's installed. And this is the system, This is the one rack, we call it one rack. And this has got like 4,000 Powerline nodes. 4,000 for Powerline nodes and 25,000 NVIDIA, 25,000 plus NVIDIA GPUs, the latest, the V-Enter GPUs, all put together, the massive supercomputer giving a, 200 petaflop of, supercomputing power for, and mostly AI kind of application and also high performance computing applications, are running on the system. So, there are lots of things, you can do with this system, and this costed around $350 million for US government, to build this supercomputer. $350 million.
This is being used by LIC. LIC use?
LIC?
Large Hadron Collider.
Yes.
Yeah, the computer is being utilized by LIC.
Yes. And there are two supercomputers built. One is for general purpose users, and the other one is actually kind of the confidential kind of under NDA kind of thing that is installed in Lawrence Livermore. I don't talk about that because that's confidential, but this is actually kind of open. Even for the researchers, we can get access to this supercomputer, and I'm very successful in getting access to colleges like MIT. MIT is very much collaborating with us, on this supercomputer, and they are doing a lot of things on that too. So MIT in Boston. There are a lot of MITs in India too, but I'm talking about MIT in Boston actually. So you see here, if you have an application which you tried it on power system and it runs very well, and if it is scalable to 4,000 nodes, you can write a proposal to me. I can get you access to this massive supercomputer. Once you run on this system, you know the power of it. Like, you know, even if it takes 20 days, 30 days for you to complete a job in a normal computer, this will take like maybe 2 minutes, 3 minutes to complete the job. That kind of, you know, the scaling, you know, you get it here. Super, you know, the super scaling kind of, you know, thing. And this is the world's largest supercomputer. And please, you know, go through the video and other stuff. You know, I'm going to give this slide to, you know, the organizer here. Definitely, you know, you can, when you have free time, you know, you can go through that. And I already talked about, you know, the Powerline processor, 27 plus, you know, 1000 NVIDIA and 4608 GPUs. And, you know, a node performance is 42 teraflops. Like that, so many, you know, things, you know, put together on this supercomputer. And also, industry researchers can get access to Summit. And that is also possibility is there. But the only thing is you got to have an application which requires this kind of system. Not a, you know, the PC. A lot of people, you know, even I do get requests from people, you know, when even they can accomplish the task in the PC, they want you know, supercomputer. That is not a reason for this. You really need something, you know, which requires this kind of highly scalable, you know, supercomputer. Got it? I hope you understand that, you know, there are a lot of things, you know, which are very important for your career, you know, I've been sharing. And definitely, you know, there will be some topics, you know, from Dr. Jayakumar, you know, where you can get some ideas about, you know, running some application on this computer, right? And then I talked about the Google, you know, the open power, you know, based system, right? This is the system, you know, the Google put together, and this has been widely used in Google right now. It's a motherboard they built, and we have a small desktop as well as a workstation kind of computer also built using Powerline processor, and we do have in India 2 of those systems, and we are trying to build something, you know, some components as part of that. Then, you know, we may be, you know, releasing that, you know, in India too. And this is the computer where, you know, you can quickly do some cool stuff, you know, as part of you know, any kind of you know, AI development. And one of the students is going to be sharing some experiences, you know, what he has so far. Is Aditya? Oh yeah, he's here. Anyway, he's going to be sharing, you know, one of the AI capabilities in this computer. Okay, and Powerline processor. So we, Professor Taki talked about the Power 1, right? But I just want to share, you know, the slide here where the Power 9 is in the, you know, right now we released it, and probably, like, you know, what is that I'm taking out right now? Can you tell me? Okay, for you to, you know, just get the feeling, you know, I brought one Power 9 processor here. This is the processor which has got lot of AI capabilities, real AI capabilities. And probably, like, you know, you can just take a look and, you know, see how it is and all. And this is heavily used by enterprise. Many banks, and, you know, I will talk about the industries, you know, who are all using it. And there are lots of, you know, innovative opportunities also around this Power 9 processor. I will pass it down to you people, you know. Maybe you can feel it while we are talking about this Power 9 workshop. So, Power 9, you know, the capabilities, you know, we have like a 12 cores and, you know, 24 cores kind of system, and you know, each core is capable of running 8 hardware threads, and that's the beauty of it. You know, in one processor, 12 into 8, how many? Like, you know, so many applications you can run on it, and usually it comes with, you know, one processor or a 2 processor. A system comes out with that. So those things also you can learn, you know, while you are doing, you know, when you are part of, you know, this open power ecosystem and all. And yeah, other features also are there, and which we talked about it already. And industries. So this is a job opportunity, you know. I'm not talking about here .NET job opportunity or Java application job opportunity. I'm talking about real hardcore, you know, innovative and development, you know, some kind of a new areas, development opportunities. see here what are the industries we are working with right now.
Is that very much open, this job of?
Yes, sir. Yes, I'm going to pass on one link also along with that.
Okay.
I created a blog and I communicated to entire world also on that. But sometimes the job opportunities may be available more in Europe and US because those are the places widely the Powerline processor are used. In India, people look at the low cost system and other stuff, and that's where the things not coming up very popular here. But anyway, we are here with the open power to create the momentum here too. So see here, automotive industry, that's a number one right now. There are lots of companies. Who is the number one automotive industry right now doing lots of AI in the world? Okay, you guys know about it. So Tesla, one of the speakers from Tesla, the AI speaker, was a part of my workshop in California 1.5 years back, and he talked about all kinds of features enable Tesla to run right now. So there are a lot of AIs also in there. Our partner NVIDIA is predominant partner with them to do that too. Tesla. Similar to Tesla, there are a lot of companies like Volkswagen, GM, Ford, and Mercedes-Benz. All these companies putting together lots of innovations as part of the car. You tell me right now, maybe just to give you some background on automobile industry and the AI. Why AI is very important for automobile industry? Anyone can answer this? To replace drivers? That's what, to replace drivers? Why?
So because if there are drivers and the mistake is done by drivers and both the car and the drivers have undergo damage. But sir, if the AI enabled car undergoes any sort of damage, then only the car is hampered. There is no driver to get hampered. So it's actually saving lives, ensuring safety.
Only driver, not the passengers and all. Right? Okay, good. Anyway, we had to clap him, because he at least came forward and shared, one of the points here. But thanks for that. It's actually not driver, the passengers. It gives more safety on the road. And if you have AI-enabled car, it gives more safety. It's not to replace the driver at all. People are misunderstanding that. And in each and every field, even hospital. The next one I have here is talk about the pharma and health life sciences. It's not to replace the doctors in the hospital. To give you more safety, secured, highly accurate answers. Like accuracy. Yeah, accuracy. That's what safety. One of accuracy is very important for our safety actually. Yeah. So in the hospitals, radiologists and all, there are lots of CT scans and all every day comes in, right? In countries like India and China, a lot of population. If you don't have automated way of checking the things, there will be a lot of mistakes. Mistakes could cause so many casualties. Like I have been reading a lot of articles in India, by small mistakes and all, lab tests and all, people die. So those things can be reduced using AI, and that's what it is. So you need to understand that it's not going to replace human beings' jobs. But human has to do more intelligent work. That is very important. Not just a phone call and answering question and then and get a money. You need to do some really thinking work, and that's what AI is going to enable you. AI is going to give you a lot of features in that. And what we have here is a platform for you to develop a complete AI solution.
Well, good afternoon now. Okay. Just before starting the presentation, once again, just my little bit introduction. I am Arghya Kusum, commonly known as Argo everywhere. So I am an assistant professor at University of Wisconsin at Platteville campus. And today I am going to describe my experiences on IBM POWER AI HPC system that accelerated some of my research on genomics analysis. And especially I will focus on their new technology of like SMT8, which is called simultaneous multi-threading, 8 simultaneous multi-threads. So anyway, and I did my PhD from Louisiana State University. So, well, this slide is giving you the brief, is the brief history of my experience with IBM. So, I'm in relation with IBM when I started doing my PhD in LSE. Well, not from the day one, but afterwards. So, when I get my first exposure at power processor, power-based HPC system, means the supercomputer. So, specifically, it was a Power 8 system. So, today's agenda is Power 9, which is the next version. But I got my first exposure on Power 8. And then I moved to University of Wisconsin-Platteville after my PhD study and joined as an assistant professor. And now we are the member of OpenPOWER Forum, where lots of different industry and institutes throughout the world, not only USA, not only India, throughout the world, we are collaborating to move ahead in terms of HPC research. For example, I am trying to move forward in terms of my own genomic research. Also, I want to do some HPC consultancy and all those things. So, well, this is the brief history of my experience with IBM. And, while describing my experience with the power-based HPC system, first I will just give you a brief introduction since there are lots of huge student population. I'll give you a very brief introduction of big data challenges in the genomic analysis. And after the introduction, I will describe one of the very important application in the downstream genomic analysis, which is genome assembly operation. How many of you have heard about genome assembly? All right, I will describe it. Okay. Okay. So, well, and then I will describe some of the. I will explain some of the results. And while describing the results, I will give you the idea of what is a traditional supercomputer. And sometimes you will get some kind of buzzwords or some catchline like whenever it comes to big data, then the traditional supercomputers fail short. Why? So I am going to give you a brief idea about all those things. Alright, so let's go for the introduction first. So where I am going to describe about what is the big data challenges in the genomic analysis. So this figure is one of my favorite figure. So where it basically shows a timeline of the change in the sequencing technology. So here, if you see the picture here, it will show. So you can see that the sequencing technology has outpaced Moore's law. Means the number of transistors per die has increased a lot, and the cost has been plummeted down. And here, plummeted down or reducing the cost, by reducing the cost I mean to say that in 2001, the whole human genome sequencing cost was $1 billion US, and from there, in March 2015, the cost has been plummeted down to only $1,000 US. Alright, so as the cost is going down, the next generation sequencing machines, which stands for the NGS, those type of instruments started producing huge amount of data. And those data are actually in the terabytes range. Now I will come to all the terminologies later, keep your curiosity for some time. The short reads, genome, everything I'll do later. But just to give you an idea that the data is in the range of terabytes. And now these terabytes of data, if you want to analyze it, it needs complex algorithms. Not only complex, your algorithm should be scalable. Means only one single node cannot analyze the entire data sets. since it is in terabytes range. Now, this big data set is actually producing a lots of pressure in the existing high-performance computing system, traditionally known as supercomputers. Well, and after this complex analysis, we reconstruct the entire genome and do other genomic analysis. Now, from these terabytes of data, if you see the slides, we are reconstructing the genome, which is basically a few MB. So, from terabytes of data to megabytes of data with some complex analysis and scalable analysis. So, basically all the computations are very much IO intensive, very much compute intensive, very much memory intensive in nature. So, whenever you want to design a software for that, we need to take care of two different things. The first one is your software should be extremely scalable. Means whenever you will add some hardware ratios, your software will work fast. Your software performance will improve. And of course the algorithmic complexity. So if something is order of 1, you need to reduce it to order of log n. If something is order of n square, you need to reduce it down to something else. So otherwise you cannot handle the terabytes of data. Well, so these are the software challenges. So not only the software challenges, it eventually we came to know that, alright, if we do not change the hardware, this software cannot work well. So the next generation HPC platform challenges are, they should support more compute cycles, means more and more CPU cycles and everything. Then extreme IO performance is also required, and also you need a huge storage space, which are like the pillar for big data analysis. Well, to address all these challenges, we got several programming models in the last few years. Well, here in this context, although this workshop is mostly focused on AI, but here I am going to talk a little bit about the genomic analysis and the big data part of all these things. Not directly related to AI, but very much relevant to the power-based HPC systems, and of course the supercomputing environment. So anyway, so here are the big data programming models that got popularity in the last few years. The first one is MapReduce. MapReduce became the de facto standard of distributed computing in the last few years, in the last decade. So what is MapReduce? Here, the computation is basically divided into two different parts. So here in the first part, that is the map phase, the user writes his own function, which basically works on each and every record in parallel without any interconnection. Ganesan has defined what is interconnection. So without any communication between each and every part of communication. So, and after this computation, they actually emits out an intermediate phase of result in the form of key value pair, just like your hash table. And after that, based on that hash, user can write another function called reduce, which basically aggregates those intermediate key value pair to produce the final result. Well, so this is one of the computation model. Another computation model is a graph processing model, vertex-centric graph processing model. So here, the computation actually move forward in the form of a super steps. So in each super step, the same type of function, the same function is basically executed on all the vertices of a graph, just like the map phase in the MapReduce model. But after that computation has been done, there is a huge message passing between all the vertices of the graph. And based on those messages, whenever after getting all the messages from all other vertices, the entire graph, whenever it is in sync, it moves to the next super step. And the entire thing is inside memory. So it is faster than MapReduce, and well, so that is the vertex-centric. So there are few examples. So MapReduce example is Hadoop, is de facto standard. Possibly all of you have heard it. And the graph processing framework, there are GRAPH, there are graphics, there are so many other things. There are Pegasus, there are lots of different graph processing frameworks. Well, the next programming model is distributed NoSQL. NoSQL stands for not only SQL. Well, so here the data is basically stored in terms of key and value pair. Just like think of a huge hash table distributed over lots of computers working as a whole. Whenever your entire data set, you cannot hold it on one computer, you are just distributing it over many different computers. You are just distributing the computation. And now, using that application programming interface, your program can get a uniform view of the entire data set, which was not possible in MapReduce or the vertex-centric graph processing. Means each of the computation phase can get the idea of one set of data, not the other set, but here it will get the idea of the entire data set. So that's the NoSQL. Now, based on the requirement, you can use different type of NoSQL. Some of them are in-memory NoSQL, where the entire data is stored inside the memory, which are really very fast, but on the other hand, very costly also, because it is using memory. And there are some disk-based memory NoSQL database also, like H-based, MongoDB, and all these things. Now, here, for this presentation, I will mostly use this in-memory NoSQL, which is one of the strong point in IBM Power H-based processor at that time. So, well, as the programming model was changed severely, the traditional HPC cluster could not handle all those things very efficiently. So the HPC architecture also started changing. So here I gathered some data from different websites from 1993 to 2012. Here you can see the processing speed of all the fastest supercomputers, starting from Tianhe to which was in 2012, something like that. Of course, Summit is not included because it was not there in 2012, right? So, well, now it should be Summit. Anyway, so here, if you see, there is a trend that the bandwidth, maybe the computational bandwidth, maybe the interconnect bandwidth, maybe the I/O bandwidth, everything is improving, because the big data is bandwidth hungry rather than latency hungry. So this is a common trend in the big data HPC hardware, and based on these common trends, all of our research are focused on, and my research was mostly focused on the genomic analysis. How to leverage all these changes in the programming model, how to leverage all these improvement in bandwidth, how to leverage all the other improvement, all the algorithmic complexity. So in the next few minutes, I'm going to describe that experience, and especially with respect to Power 8 system. How is it different? Well, so before going to the hardware details and Power 8 related results, let me describe the genome assembly problem a little bit. So the genome assembly problem, well, so there are some machines called next generation sequencing machine. So there are several companies called Illumina, Ion Torrent. You can search over internet. Those companies have changed the sequencing technology a lot in the last decade. Now, what happened, as I have told, they outpaced Moore's law. So what happened is they started producing huge amount of data. Now, while producing the data, we have to always remember that one machine, one Illumina machine or any next generation sequencing machine cannot read the entire genome in one go. So what they do is they just read the genome from random places with random depth of coverage, means starting from any sequence to ending at any sequence, many times. Well, and now the genome assembly means you got lots of scattered apart part of the entire genome from the machine, and then the genome assembly algorithm will just stitch those scattered part to reconstruct the entire genome. Now, the entire thing you have to do without any reference. So you do not have the idea of that species. So how will you get the species reference? So you do not have anything, but you need to reconstruct. So the problem is similar to a book binding problem. Suppose you have multiple copies of a torn book. So some part has 1 to 1000 page, some part has 2 to 2000 page, some part has 3 to 1000 page, something like that. Now your responsibility is to reconstruct the actual book from those torn apart parts so that it makes sense, so that you can reconstruct the entire original book. Now the idea is, what you need to do from those small torn apart parts, what you need to do, you need to make even smaller pieces. Like, let's make 1 page at a time, and then try to connect each page one by one. For example, let's say in 1 page I have written Arghya Kusum Dash is an end. Then in the page, a professor at University of Wisconsin-Platteville. So you can get some kind of connection between those 2 pages and you stitch those 2 pages. Okay, so the genome analysis problem is also just like that. What you need to do is, basically, you need to build those random parts read by those sequencing machine into even smaller parts. Now those parts are called k-mers. That's a terminology because the length is normally denoted as the alphabet K. So now based on these k-mers, the relation between those small k-mers, you can reconstruct, you can design some of the algorithms to reconstruct the entire genome. Now here it is a pipeline of a, pipeline of a very general purpose genome assembly. Now this entire genome assembly problem or this book binding problem for your easy visualization, this thing can be easily mapped as a graph related problem, a graph solution, graphical problem. Now, so here we got the terms called short reads. Short reads are those random fragments read by each of the sequencing instruments. Now, from those short reads, we have to build a graph, and then in the subsequent phases, we need to analyze the graph. Normally, we need to compress long chains in the graph into one single vertices. That's why the compression terminology is used. Now, in our graph process, in our genome analyzer, for the first phase, that is the building graph, we have used Hadoop, that is MapReduce. And then in the next phases, we have done several research. Now for in IBM Power 8, we have got the best result where we have used NoSQL based graphical analysis. Well, so I'm going to discuss that in the next few slides. So here, as I have told, so here this is in a nutshell the genome analysis algorithm, the picture. Okay, so first one is a MapReduce algorithm. It is a Hadoop. So what it does is Hadoop reads each of the short reads, means each of the fragments without any connection to others, the Hadoop map phase. And then it divides each of the short reads into even smaller fragments, which I have called k-mers, right? So just like 1 page of the book. And then each successive k-mers are can be visualized as a vertex of the graph and the edge of the graph. All of you know, I think, what is a graph representation in an adjacency list format, right? So a vertex and then a list, then its edge outgoing from there. So after doing that, we got lots of key value pairs in the intermediate part. And then in the reduce phase, what we are doing is we are just aggregating on the basis of each of the vertex, which is working as a key. So we got one key, one edge from it, one key, one edge from it. Then aggregate all the keys and get all the outgoing edges from that vertex. Well, and after that, we got the graph in an adjacency list format, which we have written in the HDFS, which is Hadoop distributed file system, which comes with Hadoop to distribute the data without knowing any complexity of the distributed file system. You just need to copy, you just need to follow the Linux command. Then after that, as I have told, I have used distributed NoSQL to analyze the graph. Now, compression of a graph that I have told means you need to traverse the linear chain. Now, that's typically can be done using a hash table. So let's start from this TGT. Let's start from this vertex and then go to the next stage and then again search for the next vertex, then again search for the next vertex, and in this way you can easily traverse the entire linear chain, and you can compress the entire chain into one single vertex, and that is going to give you the linear, the entire reconstructed genome. So that part is normally known as graph simplification, and this is a NoSQL based or hash table based approach for graph traversal. And well, so there are several other parts also, like error correction and all those things, error correction from the graph. So just for the sake of time and just for this context, I'm not going to much details on all those things. So rather we will focus mostly on the results. What are the difference in traditional supercomputer, which fits in the context of this workshop. Well, so before going to the results on the traditional supercomputer and IBM Power 8, any question on the algorithm? Anything that you couldn't understand?
So the graph compression part means we are in the software architecture part, in assembly software architecture part, you told that we are compressing the graph. Means first we are completing the graph and then we are compressing. Then that means that we are connecting the chains. Is that the same thing?
Yes, that's a good question. So I'm sorry if I was not clear about that. So whenever you will create the graph, there normally you will get a long chain of vertices. Means A, B, C, D, E, F, like that. And then graph compression means, let's say A, B, C, D, E, F are all new vertices, different vertices. You need to traverse the entire graph and you need to clump all the vertices together. So that's called compression. Since there are 6 different vertices clumped to one vertices, we call it graph compression. Clear? Alright, any other question? Alright, so, okay. Well, thanks for the question. Yep.
There is one interesting thing comes up now. The sequence farming. And you given the distributed sequences, and then you are trying to reform the sequence which is meaningful, right?
Yes, exactly.
The word meaningful is subjected to the whatever the thing which are given the hypothesis, what hypothesis is put in.
Yes. Yeah.
So that's on the formulation side. When what RNN does extremely well in that instead of a graph.
Which one, sorry?
RNN.
Oh, okay.
RNN does extremely well in the graph. Example, natural language understanding. So the graph will face one district lot of things, But the same thing is very precisely going on RNN. It has
okay.
It has a better sequence.
Oh, that's great. So are you talking about Dr. Franklin's genome sequencing pipeline?
No, not in genome. So document a sequence of words.
Just graph.
Randomly put the word. Meaningfully, we want to construct the
alright.
Sentence. So
Yeah, I got it. In terms of natural language
If
processing.
you do that when the geometry approach, you have to add up issues. You aren't that appears.
Wow, that's really nice. So yeah, that's really nice. That I can try actually. Thanks for the idea though. Yeah, so he's talking about some different type of approach. What I have talked about. This is not the only approach. Of course, I must say there is nothing called the only approach in research. So there are lots of different approach. So he's saying which may have the potential of getting better results than this one. Alright, so yeah, thanks for the idea, and I'll definitely try. We can really collaborate on that. Thanks. Okay, so alright, any other question?
One more question.
Yep.
if the graph contains multiple components in the case?
Okay, that's a very good question actually. So I do not have the detail of the algorithm in today's slide. So yes, there are lots of different chains in the graph. So for example, let me just go to this slide. There are lots of different chains in the graph. Now using the current supercomputer and those and those Hadoop and other programming model, you can compress multiple chains together. The computation for compression is going on simultaneously for different chains. There may be like, let's say 1 million chains in the graph. It's possible because there are 1 billion of vertices. So you can do like, let's say you have, in your entire supercomputing cluster, you have 120 nodes. Each node has 20 cores. And then you have like 2,400 cores. So 2,400 chains can be computed together, can be clubbed together. So yeah, and of course, after that, there are some error correction. When we actually do some error correction and we remove some of the bubble structure and some of the tip type of structure in the graph, which will generate some new chains again. For those also we use parallel computing and distributed computing to compress the chain. So this compress the chain is one of the single phase which makes genome assembly is a very complex problem, although it feels very simple. So, well, that's a very good question, thanks. Any other question? Okay. Alright, so let's move to the hardware side. So that was all about the software, and if you are really motivated or if you are really interested to know more about the software development, you can follow me on ResearchGate, you can follow me on LinkedIn. I have all the publication title at least on LinkedIn, and you will get some open source publication on my ResearchGate. You can go through that, and also I can share my email ID. Feel free to send email to me, and I can answer all your questions. Alright, so let's go to the next part, that is the results, where we are going to describe about some of the traditional supercomputer and why IBM Power 8 is beneficial, something like that. Although I will focus mostly on the computation and the architecture side, not the very lower level electronics, because my background is computer science. But if you have any question, you can ask me. I can move forward the question to the right person, and also you can ask the delegates from IBM. Well, so this figure is basically give you a very nice overview of a traditional supercomputer. Now, in traditional supercomputer, we get a management network where we do all the management of node information, management of node things, and all other system admin like work. Where, well, I am keeping it very broad level. So there are lots of different things, but I just want to make all of you understand what is happening actually. So there are few nodes which works as storage nodes, and there are few nodes which works as computation nodes. Now storage nodes are mostly used for, as you know, storing purpose. Now this storage is a little bit different from the traditional storage on your laptop. How is it different? The file system. The file system they mostly use as a parallel file system, which is a POSIX based, like thread based file system. Multiple I/O operations and all those things can go at a single point of time. So the file system itself is very fast, rather than your local file system. Well, there are storage nodes with all the parallel file system installed in it. So some of the parallel file system can maybe like IBM GPFS, which nowadays goes with Spectrum scale. So there are some other POSIX based file system also. So then the compute nodes. Now these compute nodes can be of different types. So now let's say there are a few computers. So what supercomputer I have used in LSU, for example, let's say some nodes have 32 gigabytes of memory, some nodes have 1 terabytes of memory, some nodes have 2 processors. So 2 processors with 10 cores, some nodes have one processor with 20 cores, something like that. So there are different type of compute nodes. So compute nodes mostly focus on the computation, and the storage nodes compute on the storage. Now there are some problems in this. Oh, and another thing, all the compute nodes or all the I/O nodes are connected with InfiniBand. How many of you have heard about InfiniBand? Well, in the first half of the lecture, we were discussing about Mellanox, right? So Mellanox makes lots of InfiniBand switch. InfiniBand is kind of a protocol, just to give you an idea, which is responsible for very low latency interconnection. Okay, so most of the time in the traditional supercomputer, these InfiniBand follow an architecture called fat tree. Means the switches of the network are actually hierarchically distributed. Now the entire bandwidth, let's say 40 gigabytes per second, 40 gigabits per second, or 56 gigabits per second, that is available only in the higher level switches. Now in the lower level switches, the bandwidth is just distributed, divided. It's well, although it's not a very nice example, but you can think of it as a parallel connection of electric. So where the current electricity is just dividing up. Well, so now that type of architecture is actually results in low effective bandwidth, and then there are some storage issues also. Now traditionally, supercomputing cluster always focus only on the computation power, petaflops, exaflops, teraflops, whatever it is. But whenever it comes to big data, as Ganesan also told in first part of the lecture, it should not focus only on the computation. Of course, that's the major part. But at the same time, you need to focus on the storage, means I/O bandwidth. Because when the data is read from the disk, it takes a huge amount of time. Now, whenever it comes to terabytes of data, the time is not ignorable. So you need to focus on that. You need to come up with some type of formulation how to balance the cluster. Okay, now I am not going to the formulation of the theoretical part in today's context, but I have a paper. You can get that if you follow me in ResearchGate, where I have formulated all those things. And we can also discuss in offline regarding those. Anyway, so there are storage. So normally in the traditional supercomputer, there are very few directly attached storage devices, and mostly they are hard disk drives. Now only one hard disk drive and lots of data, there are huge I/O latency. There are huge drawback, huge delay in the I/O, and that is very high whenever it comes to the terabyte scale data. And that can be, just to give you an idea, if just to process a human genome with normal supercomputer like this, it can take up to 30 days also, just because of this problem. So you need to be very careful whenever you are designing a cluster with this type of things, not only processor. The next issue is the memory issues. Now the memory issue is in a traditional supercomputer that I have used in LSU HPC, they have very low RAM per core. It's only 32 gigabytes of RAM, and there are lots of processor, Intel Sandy Bridge Xeon processor. So what happened is, there is a trade-off between the degree of data parallelism, how to collect the data, and now then also these big data programming model are like use some buffer size also. Now whenever this memory part core, whenever it is very low, there is a problem of holding the data in memory, and whenever the data held by the memory is less, the time consumed is more. Time consumption is more means you need to get much allocation, means lots of expenditure. So you need to take care of all those things. So whenever, from the perspective of the system vendor, what you need to do is, what you need to care is about, like, you need to take care of more degrees of freedom, not only the computation power. You need to take care of storage, you need to take care of memory, you need to take care of network interconnect, everything. So your cluster can be balanced. So that's the terminology called the balanced cluster. Now IBM Power 8, what I have used was that type of a balanced cluster. That one was really nice. So these are the test, experimental test beds that I have used. So these are the configuration. So the first one is a IBM PKY stands for Poughkeepsie. That's a place in New York, near New York. The cluster was set up there. It was basically a 40-node cluster, whereas our traditional supercomputer, which is LSU Supermite 2, goes by the name, has 120 nodes. And each of the IBM Poughkeepsie cluster has two 10-core IBM Power 8 processors. And the Supermite 2, they have 8-core Intel Sandy Bridge Xeon processor. So now the physical course computation, physical core calculation is given. Now here is the difference. So in terms of normal physical core, maybe Sandy Bridge is almost similar to the IBM cluster. But whenever you will focus on the simultaneous multi-threading, at that point of time, IBM cluster moves, performance is far ahead than Intel Hyperthread. Where Intel Hyperthread has only two hardware threads, which can do two different types of works or two similar types of work. At the same time, in IBM Power 8 cluster, you do 8 different hardware threads to do your work, which is very important for big data analysis. I'll show some results on that. And also, as I have told, that the cluster should be balanced. So just see the increase in the RAM and also increase in the number of disks per node. So as you all know, if we increase the number of hard disks, the I/O bandwidth will improve proportionally. Well, there are some other issues also for the bus controller and all these things, but those things you need to take care of course. But these are the overview. And now for to match with the IBM Power 8 performance, we have increased the bandwidth for the InfiniBand also. It was 56 Gbps, gigabit per second, and Supermite 2 was 40 gigabit per second. Well, so this is in a nutshell IBM supercomputer. It looks like, or almost like the traditional supercomputer, but there are so many differences inside it. As you can see, that IBM Power processor, it looks just like this, but there are so many technological changes. So here the major changes are increase in computational bandwidth. Like Power 8 processor had 8 simultaneous multi-threading. When let's say you are using Intel Hyperthread, one thread is doing the I/O operation and another thread is doing some memory operation and computation. Now in IBM there are 8. 4 threads are doing I/O from 4 different HDD. 4 different simultaneous multi-threading are doing the computation and all those things. Not only that, to access the memory and CPU, memory from the CPU, they have 16 memory controllers. In a normal Intel-based system, possibly it is 2 or 4, if I am not wrong. So that is significantly higher. And that increased the bandwidth of the memory and that improved the performance significantly. And we have used many HDD per node, then I/O compute distribution of SNT that I have already discussed, and increase in the network bandwidth. So here for the computation we have used architecture called clause. So clause architecture is nothing but there is no blocking, like there will be no packet drop for price saving or something like that. Well, now these are the genomic data set we have to benchmark the performance. We have used 12 gigabytes of data, 12 gigabyte size genome, then a 90 gigabyte size genome, and then 3.2 terabytes of metagenome. Well, so first of all, this result is the scalability result of SMT, that is simultaneous multi-threading. So here what I have done, I have used, I think it was just only one IBM Power 8 node. I started with one SMT, that is 20 cores, Then I have increased the simultaneous multi-threading to SMT2, just like Intel hyper-threading on and off. So I have increased it to SMT2, that means 40 virtual cores, then 4, then 8, something like that, and this is the execution time, which is almost linearly scalable. Well, so I have done it with two nodes. So one was the Hadoop master node and one was the computation node. So basically the computation was being done on one node. Alright, so here are some details of the Hadoop configurations. I am not going into the details of that. If you are interested, you can let me know. And this is the Rise genome performance. So here if you see, we have used the traditional supercomputer, 6 nodes of the traditional supercomputer, that is LSU Supermicro 2, whereas I have used only 2 nodes of IBM POWER 2. So here we have got 2.5x performance gain using 3x less number of nodes. So per server is almost 7.5x gain, and that is only for 12 gigabytes of data. When the data set increased to 100 gigabytes, like it's 90 gigabytes, the performance is also kind of similar, where we have used like 40 nodes and 120 nodes. But whenever the data size is increased to 3.2 terabytes, the performance is even more higher. So as the data size will increase, the traditional supercomputer with all the bottlenecks with network, storage issues, and multi-threading issues, hyper-threading issues, the traditional supercomputer performance may go down and down and down. And at that time, you need this type of next generation supercomputing cluster, where IBM POWER 8 gave a very nice result to us and helped us in our genomic research. So here we have analyzed 3.2 terabytes of metagenomic data, which took only 6.5 hours on the 40 IBM POWER 8 nodes, whereas which is almost like a 9x improvement. That was 7.5x, and here we got 9x performance improvement in terms of performance per server. So 3 times less server, and even at that time the performance is more. So here, regarding the metagenome, possibly this term is new to you. Metagenome is not like the usual genome. Here for metagenome, you just collect the sample of environmental sample from anywhere, and then you just do the sequencing using those NGS, next generation sequencing figures, next generation sequencing machines, and you will get lots of you will get genome sequence with lots of different species mixed up. Like there can be E. coli, there can be staph virus, there can be rhodobacter, there can be lots of different things. So these 3.2 terabytes of data, we collected it from Joint Genome Institute in San Francisco, and it was a cow rumen data where there are lots of bacteria and virus and all those things were there. So we just did the analysis using the POWER 8 cluster. And so here it is the 9x server gain. So this is the this is the experimental result for POWER 8. This is the performance improvement. And also we have made some other experiments with POWER 8 cluster. So the POWER 8 cluster, whenever you are talking about the cluster, it's not only about the cluster and all the only the processor and all these things. So there are the parallel file system also. There are several parallel file systems like Luster and all other different things. So IBM use IBM Spectrum Scale, which is GPFS. So normally if you are familiar with MapReduce, so this intermediate key value pair after the map phase, that is huge based on the application. Now normally those shuffled data is written on the directly attached storage, which does not need any interconnection. Now if you want, but if the shuffled data grow in size, how can you scale that? So either you need to increase the number of directly attached storage device per server, or which has a significant amount of limitation, right? So in per server, you can do like 12 hard disk drive, no more than that. If your data goes up, what will you do? So this spectral scale, this GPFS give you a very nice solution for that also. Okay, so because you can just add some storage devices in your storage network of your supercomputer and you can get more performance. And according to our performance study, there was not much performance difference between the directly attached storage device and the GPFS storage device. Yes, there are some configuration, but those are very nominal, like creating directories, different directories for different nodes. And also, they are fault tolerant, which is not possible with Hadoop. And another different machine that I have used, which was really very unique in IBM, although I did not get much opportunity to work on that, but that was CAPI. The full form was Coherent Accelerated Processor Interface, I think, if I am not wrong. That's right, yeah. So here actually IBM has some collaboration with Reddy's Lab. So Reddy's Lab provides some, so this CAPI actually uses a flash type of storage, which is in between the RAM and normal hard disk drive. It's kind of a flash storage device, which is faster than the disk but a little bit slower than the RAM. And by using this CAPI gate, you can say CAPI is a gateway. Using this CAPI gateway or CAPI interface, the data read-write throughput, the I/O bandwidth has been significantly improved. And we got a system, what the system we have used, it has like 40 terabytes of storage space in a single box. So that 40 terabytes could hold the graph constructed from the metagenome, which was even a magnitude higher because of the algorithmic things. And we kept it on the CAPI storage device, the flash storage device, and then we have analyzed it using the Powerline processor, using the CAPI interface. And that type of processing was kind of, at that time, it was kind of impossible with our normal supercomputer. And this SuperMIC 2, which was not possible. So here are some results in terms of throughput or I/O bandwidth. So for example, it gave us like 154.4K records read and its write throughput was like 154.4K records per second. And in terms of gigabytes per second, it was 1.13 gigabytes per second, which is not very common in the normal HDD or anywhere. There are several other competitors like NVMe SSD. There are several other there are several other technologies like NVMe SSD and all those things. But their performance is also a little bit lower or similar to this CAPI device. And here, on a single machine, when we have analyzed that entire metagenomic data, it took only 7.5 hours, which was not possible using the SuperMIC 2 cluster. So that was one of my very good experience with IBM. And so that's about my first experience with IBM that I have shared. And right now I am collaborating with the IBM OpenPOWER and working on some of the genomic research using AI and machine learning things. Before going to the acknowledgement, any question? Any question on the hardware or anything?
What is
Yep.
This genome analysis, what is the aim? Can you give us some aim? Like, what do you intend to do with this genome analysis? Are you trying to find a kind of effect of medicines on the genome? Or, just not studying. What is it that you are aiming?
I understood your question. So, here if you see the acknowledgement, we have some collaboration with the bioscience experts. So they are working on the biology related field like personalized medicine. One of them, so Dr. Joo-Hyun Kim and Dr. Nayeon Kim, they are actually working on personalized medicine. And Maheshi Dasanayak herself, she is basically working on finding new human species variation. So that is very important. Like there are so many different types of human in the world, and what are their characteristics basically. And based on that, how can we identify them, and how can we prepare some kind of genealogy study or some kind of genetic disorder in those type of things. For example, in some African tribes, they are more prone to some types of disease. How to cure that? Which part of the genome is really responsible for that? So Dr. Dasanayak is actually performing that type of study. And Dr. Donga Ho, I'm not sure about his current study right now because I'm not working with him right now, but at that time he was working on cancer detection. Sorry, not cancer detection, but cancer cure. So how to do some kind of cancer related study and how to find which gene is basically responsible for the cancer study. So those are some of the motivation. We are doing only the algorithm and all these analysis, and based on that assembly is not the only work. We have all different type of suits. So based on those, these bioscience experts used it for many different purposes. So did I answer your question?
Yeah.
Okay, thank you. Well, any other question?
There are a lot
Okay.
of genome research lab in the world actually, and it looks like many of you may not know about that, but Dr. Agro, shared a lot of his experiences with that, and definitely, one of you could go and look at, Google and find out more about it, and it will be very useful for you to do, the future genome research in the medicine. Finding a new medicine or drug discovery, and many things you can do as part of that.
Well, yeah. So that's a very good point, Ganesan. Thanks. So genome research is one of the leading research problem nowadays. So there are several projects called 1000 Genome Project, 1000 Human Genome Project, Connectome Project. You can search, you can get these terms from me, we can discuss. And 1000 Genome Project is the largest project worldwide which is actually trying to find out different species of human being. Then cancer cure is a very trusting problem nowadays. And Open Connectome is going to another level details, which instead of doing the genomic analysis, they're doing lots of RNA type of analysis and all those things. And all the leading, may not be all is a misuse of terms. So many of the leading software industry, software companies, starting from Google, of course IBM, Amazon, they are all somehow related to all these type of projects. Facebook is of course one of them. They are trying to find some kind of genealogy and trying to connect the social network people and all those things. There are lots of research things going on, and these research labs, as Ganesan also told before, these research labs are completely different from these software systems lab or software development lab, like service industry. This is totally a different set of industry, which is in dire need of many good students, which is in dire need of very nice talent pool. And that is actually one of the biggest motivation of this conference, is to give you the exposure of all these research related things where you will get lots of job opportunity in your future. If you start working from now, you will get lots of different opportunities. So genome is one of them, and of course before ending ending it, so genome is not the only one application. big data and supercomputer or IBM Power 8 or anything, they can be used for different type of applications. For example, I am trying to collaborate with the scientists in India, like Dr. Taki and everyone, like on nanoscience research, and also I am talking to some other collaborator for genomic research, and also Ganesan told me about some construction related research, which is material genomics, which is different type of thing. So yeah, we are open for collaboration. If you are interested, just send me an email. And yeah.
What about medical imaging?
Well, that's a very good question, sir. So, well, our research group is really here. So our research group is really big. So Dr. Sian Jong Park is my advisor, and so Dr. Richard Platania, Sayan Goswami, and Deepak Singh. They are working basically on the healthcare, medical, image processing and all those things, and medical imaging, detecting the cancer cell and all those things.
Computer vision.
Yes, yeah. Here I would like to actually share one of the news. One of our paper actually published in ICDCS last year or last year, where we have done some kind of deep learning framework evaluation or benchmarking on different type of hardware infrastructure. And here I would like to say that IBM Power 8 or Power 9 with the NVIDIA GPU won the race, because they have a very nice connector between the IBM Power 8 and NVIDIA GPU. That is called NVLink. That's a bridge between the IBM Power 8 CPU and the GPU, which is very uncommon and very useful for the machine learning purpose. So for the training of the image, as you have asked, it can take days sometime. But now with this type of technology like NVLink, Power 8 or Power 9 right now, NVIDIA GPU, it can be done in minutes. So this type of work they are doing, and I am also collaborating with them right now.
One question.
Yeah.
Is related to, not related to big data or related to medical science. Where exactly we are standing in terms of gene editing and gene stitching and all?
Well, so you have talked about very futuristic question. So well, in the last few decades, just let me give you a broad overview. Last few decades, I was talking about NGS technologies, right? Next generation sequencing. So there, the major motivation was to find different type of variation. After that, now the technology has changed. I think I have discussed about it in my last lecture, that the read size have been improved. So the technology has evolved in such a way so that now you can get better genome finishing. Now better genome finishing means you can do better stitching and all the things better. So the technology has been changed already. After finding the variation, we are right now working on stitching and finishing the genomes, and which will be used possibly in the next 10 years down the line, or 10 or 20 years down the line. We are expecting to do some kind of genome editing other than cloning.
Because one place I have read one blog, it is sort of fiction sort of things. People are telling that if you want to die or not, that will be optional. If you choose to die, you will die.
That is there in 2040, that kind of thing.
That kind of thing. That's why I told you about the 20 years down the line.
If you choose to die, you will die. If you choose to die, you will be there.
Yes, that is.
That's what they're doing.
Yes, no, it is going to happen actually. It's going to be like that.
That will be possibly.
Yeah.
That will be possibly to the leader of the government like you, whether you will allow that type of research or not. Population problem, yeah, of course. Yes, so in the next 10 or 20 years, I think there will be lots of changes.
At that time.
Yeah, she is
faster than you.
Yeah, she is a good question.
Yeah, that's a good question. Thanks. Yeah.
Yeah. So can you go back to the
the page where you compared the IBM Power 8 with Intel Supermicro.
This one, yeah.
Yeah. So you have compared it in terms of say nodes and time consumed like this. Not this one. I think the previous
Next
one.
one.
Oh, I'm sorry.
Next.
Yeah, this one.
Can you tell me how many basic transistors has been used in the 2-1 and can you tell how long it has taken or how much power consumed for the total computation?
Well, that's a very good question actually, but unfortunately I do not have any answer for that right now.
Actually, did IBM Power 8 that did it better than Intel in terms of power consumption or number of transistors?
No, see here, let me answer that question
Yeah, sure.
clearly.
Yeah.
See here, he's talking about, full systems capability, not only, the CPU centric. We have been telling about that actually. So you are now again, the CPU centric, maybe, the Intel may be better on the CPU centric. But when it comes to systems capability, like he talked about the storage I/O, network I/O, a cluster, and then the stack of the software and everything.
Is actually clustering the things.
Yes, that's right. A complete the ecosystem. That's why the OpenPOWER plays a big role here. And even all the technology, whatever is shared, NVLink, OpenCAPI, all the stuff, PCI, Gen 4, all the things comes from this OpenPOWER stack.
So actually, you can if you just totally put together all the Intel CPUs, you will do it better.
No,
there is a.
that's systems capability. When it comes to systems capability and then the openness, now the OpenPOWER gives a very good platform for specific application, especially the genomics based applications runs far better than the x86 platform. I should not say Intel, x86 is the common word here.
Well, just to add to Ganesan, so this is the result that we have got from SMT8, and I would like to say about a cluster from Intel. Intel came up with more than 4 hyperthreading nowadays. That is more than 2 hyperthreading nowadays. It has 4 hyperthreads. That's called Intel Knights Landing cluster, Knights Landing processor. They have 4 SMT. Like IBM has 8 SMT, they have 4. So I have a chance.
It is all depending upon the number you are clustering.
Yes. Right now I am classifying on the number, and now I have some experience with that Intel KNL cluster also, but yeah, I did not get much better result on that. So yeah, rather Power 8 was far better. And now if you are interested to know about the chip level details, well, I am computer science, so I am not electronics. So yeah, if you have any type of question, just you can send me an email. I can communicate you to the person who knows about the chip level details. Well, thanks for the question, by the way.
Yeah, Dr. Das, regarding your the publication and the team, bring up the next, yeah.
Well, these are the
other one. You just open it. No, faculty. This one here.
Okay.
So this faculty and staff of LSU and UW. This is. But this data and other things. Where from your?
Oh, okay, that's a very good question actually. So the most of the data that I have used, that I have shown here, one of the data I mentioned the source, that was the JGI, Joint Genome Institute from San Francisco, which is the top-notch research lab in the genomic research. We got the metagenome data from them, but otherwise, all other data set that I have shown, those are openly available in NCBI website. You just need to search with the SRA number, that is called an accession number. You can get all the data from there.
those are all openly available.
Get me the publication.
Oh yeah, sure. Sure, yeah, I should show that. Okay, so these are the related publications. So this work has been previously presented in Supercomputing Conference of workshop, IBM Workshop, which is a top-notch conference for supercomputer. And then we have presented the similar work in IBM Interconnect, and then also in our previous OpenPOWER Summit. And if you are interested in the white paper out of this work, you can go to this website. So here is the bold one. All right, so any other question? Okay.
Very good one. Thank you.
With a standing applause from all of you for Dr.
Thanks a lot. I'm really feeling honored. Yeah, and I will be happy to work with all of you. And I really want to work for my country. And I would really like to collaborate with IBM. And through IBM, I would really like to collaborate with the professors here. And would love to work with these motivated students. And that will be a really great service from my side for my country. Great. Thank you all.
Good afternoon. Yeah, I hope everyone is back and with a lot of energy to do some lab as well as listening to some of the key technologies going to be shared by Dr. Jayakumar from Bangalore, and he is one of the technologists, and he understands the complete AI ecosystem as well as the enablement, and he has been spending a lot of his time on startups, and even he is running his own couple of startups, and also he is mentoring many startups in India. And I welcome Dr. Jayakumar to take over the session, the rest of the lunch, and the rest of the afternoon, and spend time with you guys, and with the power technology, he is going to be enabling you with all the AI features. Dr. Jayakumar, welcome you to the session.
I come from Bangalore today, so I'd like to get your all of your attention just for a minute. Just stay for the, for a minute silent for departed soul or coffee day founder. He was one of the top in class entrepreneur by according to Subarto Boxy. He wrote a book called High Performance Entrepreneur. When he was young, it's just getting to Bangalore. There are role models for us to start the companies. I'm talking with 2000. So coffee day is one of very example for us when we were young to go along, create enterprises. But today he's not with us anymore. Just for a minute, you should take a silent. The next thing, I have a big list of thanks, but however I compress that list also. I would like to thank Professor Taki and also Arghya for illustrating a kind of mind-boggling introduction to the genome-based research all over the world and state of art what is there in the US. Today we are lucky to get from you directly. I thank you. Hope he does work with us. Often we get more and more benefit out of him. Thanks to Ganesan for his kind of willingness to come be with us, though they have a scheduled power around the world globe, you saw. So
So he took out, so let's go, kind of Indian big cities and, be with the children, record some time. So I thank for him for taking that. Of course, thank this institute. Before that, Saha sir went out, I think, thank for him as well. IEM and the principal is there, is very interesting. I had a good discussion with him. Thank you for this. And also, the IEM management for giving this kind of innovative leadership here in Calcutta, taking up, looking at the thing, what's going on the edge. In fact, undergraduate, we have things, boundary value problems. When you solve the boundary value differential equation, in the middle things will be smooth is good. The issues are happening in the boundaries only. Today that's happening in the edge computing, so that's going to be a theme of class, what's going to happen edge, how and what. So we had a traditional presentations and workshops which is there, but luckily I interacted with the students and some of the faculty here since morning that given us a kind of guideline to how to organize and quickly, whatever the limited time we have, another 1 or 2 hours, to present what are the things which we can avail quickly without much investment in like as a research as a free and open source. That's what it is. That will give the guidelines and how I use it, how you can use it as well. And also I want to address few of the questions which we have been since morning we're talking about it. Here some of the students asked the question about the model, which model is deployed in IBM, whether I have a custom model can be deployed. That's a fundamental questions. Of course, that's opportunities there. We need to develop the model. It's not that all the models are out there. We have a custom model uploading also there. Models are built. Of course, some of the other, she also asked the question. Models are built in different frameworks now, but the popular framework which we know, Keras, TensorFlow, and the top of it Keras. So that's the place models are built. Once you build it, then you can execute that model on the device. You can see GPU or a CPU or FPGA. Today we forgot.
Sir, do we have the provisions of choosing whether we will execute it on the GPU array or on the CPU computer?
Exactly. TensorFlow 2.0 beta 1 you can do. You can do the right side, or you can put it what device also you can execute. Okay, that's the beauty of that. At the right side you can see what device that your model, not only model, part of the model. Suppose say convert 2D, suppose say an RLNU. So they're pulling. There's some you want convert 2D only run in a FPGA. Sorry, GPU. REL you want to run in a CPU, you can do that. Okay? So that way you can almost customize where you want your things to run also. Okay, that's a beautiful thing. Of course, there is an interesting platform, two competing platforms inside IBM. One is that Power Visual Stocks is really easy. In fact, you will ask, he done it very nicely with the third year mechanical engineering student. He used that platform and he done that classification of MNSC. MNSC one of the popular high-level program in India, so he's done that. Another one, Watson Machine Learning, that we call WML, Watson Machine Learning. In that we have Watson Studio. You can do more on that Watson Studio. It's open, so you can.
What is it?
WML, Watson Machine Learning. That's one of the popular thing is emerging out. There you can have your own model, or you can use the model existing, or you can build your model cell also there. Like Google have a Play Store, so you can put your service microservices also. Then the question came up from chip to applications. That's what I want to invite you all to think. The bottom of the pyramid we have processors like a CPU, Powerline to CSC now, and also we have GPU aside from the Tesla and the lowest whether like Jetson Nano. These are things are happening in GPU side, and FPGA there is Alveo. There is some more things are happening in FPGA. In FPGA also very interesting for computing in the real time. Suppose today I was very interested to meet our gentleman. Your good name, my dear?
Antapa, sir.
Antapa. So he's essentially an intern here in this institute. I learned that he's more and more doing research in how to store and distribute the media of high content out here. So that's exactly happening when the camera is clocked with so many gigabits of pixels coming every minute. That loading the whole video there, do the intelligence out there. The watchman is watching in the gate, so he is not sending everything. If someone comes early, he'll call us and tell. But today, video surveillance systems send everything to our disk. It's our duty to keep showing that who is coming, what's going. So that's nothing to do intelligence today, all video surveillance. The video surveillance is going to be redefined with the machine visions. So there, the bottom line can be any of these three. CPU from 922C, GPU from V100 or P100 from Tesla, NVIDIA, or LVU, of course, interconnect cards from Mellanox. This is what the thing. Maybe this is our friends from Tech Data. They're our partners from IBM side. They can share with you this very intelligent things all brought in a single page. So that's the place which is put in all the configurations, what's required in the connection, everything. You just look at it. There's very nice things for you to do that. Of course, here only the chip, when you have the chip, there is not too much of, things are happening around that. But in India, we have semiconductor, we are not ahead of America or Taiwan or Malaysia. So we are in the OS level onwards. So even motherboards are coming. That's what Narayanasami was Ganesan telling morning. Sambina was trying to do the motherboard supercomputing. So the motherboard industry is also getting well in now presently in Bangalore. I'm sure it's going to spread all over. So take the CPUs, you can plug the CPUs. You can plug the CPUs access. So this is the we are lucky to see that the first PCs come out. I don't call it PCs. A community computing system come up in a lab in Bangalore just few weeks ago. Just booted up. Things are coming well. This is, you can see it has a certainty desktop environment. It's essentially open and free. It's built at the top of Linux. Of course, we can run it in Ubuntu also. I'll invite many of youngsters learn to put more of Red Hat in it. Bigger opportunities emerging from us, device drivers and development Red Hat on it. So this is the anatomy of the PC, where you can see that it's a traditional computer. Looks like a traditional computer. So it's not like server means great, as a kind of misnomer, correct? It's not an AC room. It's just there on one of the tables. It's not a non-AC room. Of course, Bangalore weather is reasonably good, but that's the way here also fine. It's not a much. So the things is happening around the hardware also. So this is a place, if you see that CUDA, some of the engineers students are asking, this is the language. So we have enough examples, stories. There in this folder, you can use this one and then do more and more. You can do a head-on start. The CUDA basically is a kind of assembly language for programming GPUs. So that's a lot of examples are there in finance, healthcare, and all the segments it is there. And then of course this is a popular one, Power Visions, which is pretty money with it. This Power Visions what today, Aditya shown today is from the machine which is there somewhere in the cloud, a Powerline machine. But this can be on with you itself. The whole tool set, I think academic is free now, the connection.
Yeah, exactly.
Academic and research, they made it IBM, thanks to them. They made this Power Vision is a free and usable thing. So this also coming along with that. These are the two things. Because when we were young, maybe I should say one other thing. We just trying to do in master's time called MATLAB. It was just coming then, someone for years used to do. So when we take a nice printout and then go to process, they used to get angry. No, why to go and do it hand like a body plot? Suppose a body plot, you have to do it ourselves. So process is not happy when it was body plot with MATLAB. But now you see MATLAB become default with digital signal processing. today AI, the what I see in my own age today, this kind of tools like power missions and this are all become like a magla for future simply. That's exactly you could see. Yeah, here you can see all the people in one place. See.
This is the Powerline PC, Powerline 2C, latest one. And this is Jetson Nano.
The blue is Jetson Nano. You can Google it. Thank you so much. So nice job. This is a Jetson Nano. I'm sure most of you love to jump in. This, it's from NVIDIA. There you can develop all the model in power, and then we can drop it there. This is not model development platform. This is not model development platform. This is a model deployment platform. Inferencing. That can be edge. This can sit in the edge. In the red box inside we have FPGAs from Xilinx. That also the smaller one. So these are all become a computing at the edges. That's what we call. So it is not a server. This is like totally distributable form. This can be kept in any normal shop. If they want to do AI prediction, AI related thing, this whole system can go. This can be kept in the cameras or real-time data like sensors, IoT sensors. These all can jump to the FPGA board. Jetson Nano can do some kind of number crunching as GPU, and this can give you the platform in which manage the whole thing as a CPU. This is what presently is it just.
You want to mean that GPU can be kept outside?
Yes, now yes. So now yes. See, it is totally different part. Now it is here.
And then the connector and all, there will be bottlenecks, no?
Yeah, the ecosystem coming, sir. Ecosystem coming. Because in fact I tell you one few years back, IIT Kanpur I went for a presentation. In Bombay, when I was talking to Professor Naidu, Bombay forgot my power card. When I went there to the power card, I couldn't find whole Kanpur Dell power card, right? So you have to remove this PC, take the hard disk and put in another machine with it. That's it. I mean ecosystem. But the ecosystem build up, that will come out. I don't think that will be a problem. But today, Jetson Nano runs in Ethernet view. If it's the LAN you have, it's a LAN on the home you have a ADSL point, so they have a LAN, so you can put it in the
So is it complicated to set up the environment for Jetson Nano or to configure it and to put it to use? Is it actually difficult?
Okay, that I can share with you if you have your ID. I done it myself, so I have that whole worksheet from I took 2.5 days, maybe 3 days. It takes 3 days. I took it. This guy runs something called TensorFlow RT. Right? TensorFlow RT. TensorFlow RT called real time. Right? That TensorFlow RT runs this. So we need to put our model onto TensorFlow RT. We have a model in TensorFlow, so that the same thing may not be able to go quickly. So we need to set up the environment such that once we do it, after that we will. If you open to 18, so of course I done it in a couple of months back. That time I was running open to 14.04 and took me quite, but 18.04 should go right forward. So. Of course, look at the complexity. This is what there in that. There is no AC room, there is no specialty. This is what I first seeing is a lot of colleges, professors, and teaching faculties that can have their own cognitive computing system on the table. They no need to go for inherit it there to your find out setup. Of course, the parents are little capable. Now we can buy our system in our home as well. Okay, that's the kind of students can do. So this is of course Ganesan and the team OpenPOWER team is they want to make this as a kind of computing infra for AI all over the world. It's happening. That's the kind of thing. What we see is clearly that, as he said, one is in Chennai, near IIT, the another is in Bangalore. So these two systems we try. So if any good intern want to come come to Bangalore for a couple of months who knows Linux Red Hat very well, we can allow them to work on this things. Because open source software systems are not very strong now, it's a very new things for current updates, so hopefully you don't find many people supporting this right now. Of course, this will be done with that copy the If any questions there on the kind of platform for managing with ease, that's what I trying to cover this one with the existing one, what we created presently by using IBM's Powerline Processor CPU with Ganesan Nano and then Alveo from APC. That is, there are 3 people put together. If you have any questions, there we'll take it, otherwise we'll take to Daniel. So this Devi took it because a lot of questions came, so I took the last time, and so this is not part of my presentation, but because questions I took this page. So importing models saved in this is called PMML, like a model, like markup language. One machine learning machines inside that Watson or Power AI. If you do that, next week no need to go. In fact, some of the students said they want to work from smartphones. They said this one, why they need this? I can work from smartphone. They said this one can do it from smartphone as well. I saved this link to you. So this is essentially going to Python. Apart from that, you can have, this is a history. If you have old models of IBM or some business people, they have a Spark MLD. If you want to bring those models back again, for this you can try this also. Of course, Skykit is very popular. Like how Keras is popular for DL, I mean deep learning. The Skykit is very popular for machine learning, but IBM essentially ported that one in GPU also. So beautiful thing out there is Skykit now, presently what IBM offering it. They put it into GPU as well, such that your computing efficiency goes up quite a bit. After this example, I was telling you the sample Spark for regression. This example which is already there for you. So she was asking the questions, what you can do CSV file. So this example, if you took this, you can directly go there. So code is that you. So other thing comes with interfacing. So when you build a model, when you do the how-day interface, there is options are there. You can model builder to Watson Studio and then Python client. Someone says that I run the client in different things, so it can be in Python client. And of course, even if you don't want a Python client, you can go command line. That's called CLI. In the CLI, the beautiful thing comes from the guys who work on Linux, they love the CLI. CLI, you don't need to open up anything on terminals, this kind of terminal is enough for you. This kind of terminal is enough for you to finish the most of the work as such. So that's all the 3 popularly supported here. CLI also supported. If you then one more another thing is which you can have a repeated notebook also in this. These steps are given very clearly. If you have any difficulties doing that, you can please read this, because I don't want to repeat it again. It's well done. You try this. In case any problems are going through that, you can do it. So most of you can. So this is the way you can reach it out. How can I check this mail? It's not a corporate mail, so I can easily check this mail easily. I can support you also. Take care. gmail.com. So, okay, your question is. My question is,
probably you are using any kind of notebook over here.
Yeah, there in that model, the WML model. Yeah, you can use. Here, the model which you have the interface technology, when there is a Python client, you can have a resource as one of the notebook also. But that will be there will be building. So but now I may not, maybe company thinks you can do, but the students you know to do. That's the reason I did not tell you. I bounce more on a CLI and quick. Otherwise that will happen when you run this notebook on the Watson, then that's a billable item, right?
The place, the environment where you were writing the code, it's offered from IBM.
No, I just took a local notebook. Just put my address, right? Okay, yeah. This one you are talking about.
The previous window. This one.
This one I just took a notebook, like instead of PowerPoint, I'm using this. Okay. As bad as stopped using PowerPoint. Get this, we can integrate the computing and presentation together. So and also we can document. At the end you can create a wonderful PDF also if you want. See, you can export it. Export notebook has so many options. So you can really nicely do that one in one place. So PowerPoint, I just click on that. You can export HTML, PDF, LaTeX. If you want to send a paper in IEEE research, you can export in the LaTeX, and then you can find to it. You don't need to rewrite whole text. That's of course, this is I'm sure most of you know this is a Jupyter lab. How many of you have Jupyter labs? Okay, good. This one TensorFlow 2. Yeah, TensorFlow 2 Jupyter lab is really nice.
But we over here prefer using Spider rather than Jupyter.
Okay.
We take into account the IPython debugger.
Okay.
Because of that. Otherwise, it becomes a little tough using notebooks because we don't have that IntelliSense property. So a lot of us nowadays, around my community, we are shifting into PyChart, another Python.
PyTorch.
PyChart.
Yeah, my son, younger generation use PyChart, I know. But that is a little tough for us, our age, we have to do little tough. But maybe PyChart is younger than I like that. That's good for it. That's little different. You can share and then communicate. Correct. Okay. By assuming that we go to the story of it. I want to rewrite the story what the presently morning he has done MNST. So maybe I just took the one. This is also I done it because there are questions come from younger generation. This is your attention particularly looking at this. This MNST model. It's a data set. Yes, the data set is a popular one, RRC model. The morning question to him essentially what model you have. What is that's the data set is available. What the model we use to train the thing? That's the question, right? So then I just pulled out one of the example which is not available now. It's done in a Keras. So this can be done, but under the same model we can export it to Power AI also. Okay. So this I'll just step through that for your so we just gathered the data, right? Now we just got the data of 0 to 9. So we created basically what happens when the data sets are available in the different format. So we had to bring it to the NumPy array. NumPy array. And then that array we had to do then one more thing like a pre-processing. You can scale it down and normalize. Most of the accuracy of the results coming on the pre-processing only. Otherwise, if you do just that, accuracy it will be really bad. So, and moreover, one of the boy, I think Mysore, what he did was put the color one. They put the color one, then try to recognize. It doesn't go through well. It's the white and black, right? So there's a lot of pre-processing and modeling things has to go on the data itself. If you assume that you are done with your data set ready, then we can go to next step, right? Now we have a data set in terms of array. You can read the right from. May not be visible from there. Correct? Now it's visible. So this is exactly we step through that. Now next we go for normalizing. The normalizing in the place LADA signal processing people comes. The word knowledge and image processing essentially comes to this place only. How we bring this data into the, I think people have different normalization scale or picture to picture or handwriting to handwriting. It's a quite a debatable thing. But one type, assuming one hypothesis, then we can go and normalize it. After normalizing, we got this. Good afternoon. Yeah. So this is a place encode outputs, and what happens is this is what we talk about encoding part of it. When the as the labels, when the data sets of independent, we don't have labels, unordered data sets. They are spread across any places. How they are not ordered data sets, correct? They are not ordered images. But for us also looks like 0, 1, 2, 3 ordered. But in a computer algorithm doesn't know it's ordered or unordered. So we look at that way. Then we, as a human being, has to intervene here. That's a place people bring out the knowledge here. That's very easy way to call labeling. Otherwise, we have to put a hypothesis in the formal language of automata. We need to say we have to generate hypothesis out there. Then we have to stick out to the hypothesis when the inferencing coming out. So basically, hypothesis set ready for inferencing. Otherwise, in normal language, we call it the labeling. So we now label it 1, 2, 3, 4, 5. But otherwise, the hypothesis.
Then we need to remove the bias regarding the labels as well.
Yeah, of course, that's why I said we were normalization here to a lot of filtering. I have another example, I'll show you that. That's a healthcare example. This is called that question. So, this is essentially kind of data flow which we are talking about. So, it's 60,000 files. 10,000 files. These are reasonably okay. It's not a Today morning, he was talking about their universities have 4 terabytes and files, so how things go smooth and difficult. But since it becomes a smaller, locally feasible, this 60,000 files are reasonably possible, so we are going with that. This is the most contested place which is coming from the use of models. Of course, I shared this example. I wrote a lot of commentary on that. I shared with you. See. The modeling place, people differ a lot. What happens is, modeling essentially CNN convolutional neural network. People can have. This is called sequential neural network, right? Okay, Keras provides something called sequential network. The sequential is a place provide the option for us to compute it differently parallel. Morning was telling now we have to map reduce. You remember? So this is a kind of pre-processing done for map reduce. The things are really done. So this convolution, if you want it to 32 filter, see the convolutions here. The convolution, if you see the first, there is a 32 filter. So each filter is independent. So it can parallelize 32 convolution instant you can run it.
Sir, what do we mean by this 32? Could you please tell again?
Okay, see in the formal language of automata, we call that is essentially kind of learnable items. What we can learn from the picture. There is a picture is the image. What we can learn. That's called learnable parameters. The parameters can be learned. There are some parameters cannot be learned. So we assume that 32 parameters can be learned from this. In the normal language called feature vectors. Correct? The feature vector is the normal language which we do. That is the part of machine learning world. But in the deep learning, we don't use called feature vectors. Feature vectors are invented. Here, the duty of that is to invent the feature vectors in the given image file. In fact, that can be parallelized massively. That normally people do 128, 64. The bigger pictures, even the 512. So you can 512 nodes, you can parallelly start that. That's the beauty of Keras. Why it becomes so popular, like revolution all over the world was it is split in the architecture of what we talk about Powerline GPUs and FPGAs. So then, if you want to do the max pooling, flatten, these things you want to do.
So what about the 3x3? Is it regarding any convolutional network?
Okay, good. So what is that?
Our attempt is to create a convolution neural network.
Yeah.
So is that 3x3, by that 3, 3, do we mean that we have a 3x3 matrix which would we bring into convolution to all the features?
That's exactly what I'm telling. It's called kernel.
Yeah, that is
the convolution kernel. That's it. I want to give you a little introduction such that in undergraduate you would have read in signals and system course actually. In the signals and system course our professors would teach us the following way, right? Correct? This is what we do in regular signal processing, right? One dimensional. We have a input as XRB and output is Y. This is what we learn, right? This is what we do in normal signals, whether audio signal or a speech signal or a sensor signal everywhere. This in the conventional language called filtering, bandpass filtering. The another language also pass band, bandpass, limit. Everything the whole of signal processing was revolved around this, right? But what happened in image processing, they brought a spatial dynamics. So this will become literally speaking. This will become T tau 1, T tau 2, right? That is because of we have X and Y. I'm saying what happens is the question is 3x3. To answer your X is 3x3. Here, how long we hold this data? This is the convolving. Actually, I should have convolved with this way, right? Okay, I would have convolved. This is the correct way, right? What happens is this is a window, right? This is the window we are going to have that. How long that window? So this is this is a T1, T2 going there. Whether our window is this much, or our window is this much, or windows. This is the window length, right? That's how we are going to sample. For example, speech signal processing, we take 160 samples as our window, right? Or for narrowband coding. So then this will be 160 sample X will come immediately go for the convolution. So here what happens is there is a lot of researchers, of course, different applications. They study 3x3 up to 7x7. But there is no fundamental scientific research come out today what could be the optimal kernel size. Every lab, they have their own versions of kernel size. There is no research says what should be this kernel size. So that's an open problem, research problem still there. What could be the correct kernel size for a given problems? But what has an ad hoc kind of thing? So 3x3, I'll try 5x5, I'll try 7x7. But I'll give you another example there where a lot of things will happen. We'll hold that. This also for an exercise. Okay. Yeah, image processing is coming back in big way. It's not going to leave us. So, assuming that we got the model, of course there is a model also, that's a layers, right? This is a one layer. We can think of this whole thing as a one layer, right? You can have multiple layers. Layer 1, layer 2, layer, as much as possible before we go for inferencing. This is our input. So again, this is the open problem. Second open problem is now there is no scientific theory says that how many layers. Layer 1, layer 2, layer 3, layer K. What could be the number of layers required for a given input set data to arrive this hypothesis called inference? So we are going to infer the kind of hypothesis. The set is bounded, but we agree that that's one. Data is too much. So what could be the number of layers required for assuming that this is given? This is given. What will be this? We don't have results for that today. But an industry people go with on a research also goes lab to lab. That become a confidential also. Maybe they will not tell how many outside. Because people are not going for a patent nowadays because they know this is the result they're coming, this is coming. So that way I'll tell you the probability of not the success coming by selling the neural network weights. And what could be a sellable item is the whole problem. What could be a sellable item? Sellable item is This is all called graph and its weight. This is what cell level item. Suppose you want me to deploy this in Z and nano. If you give me this graph and then weight, then we don't require anything. As soon as input comes, goes through this graph with the respective weight, then output comes.
Sir, what do you mean by the graph in this case? I mean, what do we need to be provided for implementing the graph?
Model, this is the model, correct? We agree on this model, correct? The graph first is convolution 20 close, second thing is multiple, third thing is a flattening, and then fourth dense, and so.
Sir, you said that if in case of Jetson Nano, you are provided with graph, one is provided with graph and the weights, then he doesn't need anything else to execute.
Anything, we don't want anything else from others to perform this inference.
And so, what do you mean by this graph?
Okay, let's say graph. See, the graph essentially, this is the graph for us. In the language, what they use graph theory, electrical engineers like Vertex and Node, this is not a graph here. So please assume that this is a graph for us. This is actually a graph in the sense the data flows from here. Let's assume that it's a neural network, simple neural network. So that it goes here, right? So then we have a weight here, right? So, but instead of that we have convolution 2D here, right? That's why instead of this we have 2D. 3 cross 3, 4 cross 4, but like that we have 32 filters, right? So this is like a 3 cross 3 filter, correct? Like that we have a 32. That's what it is. That is. This is 32 learnable features. We assume that we are going to learn 32 features out of this input, and each feature is 3 cross 3. That's the outcome now. Okay? So similarly, there is a other state. Here is like once again there is no theory behind that one. Something we are missing. Then we move next one. Okay, this is a model. This is an empty model. So any graph is defined. This is what defined now. But what is not completed, this is done. But this is not known now. That's what we want to complete. Where the hardware today, Powerline and IBM, all this, NVIDIA and Xilinx, all of them computing it, how to compute this weight efficiently within shorter times. The graph is the one, guys like you are, as we are going to give. This is the IP concept. As soon as graph defined, this is also known, input also known. How we are going to compute the weight in the given shorter time with minimal expenditure. Imagine if you run this one, the regular computer on the cloud, it might take 10-15 days. Our credit card is gone, correct? So that's the place now. A lot of local agents and so on so is coming out now.
The weight usually is calculated by the back propagation.
Yes, sir. There is a method, sir. That is correct. What sir is asking about the back propagation. Here now is called convolutional neural network (CNN). So here this is first what is the idea? Randomly initialize these fellows. Randomly initialize. That also a lot of guidance are coming in that. How do you initialize? What is the starting point of this weight? You have to start with some place. That's not 0, 0, correct? The 0, 0 weight is build one case and it. W11 right? This weight need not be 0. If it is a fully 0, there is no problem. So we level random weights which we are choosing that. In the random weight choosing, the problem comes is essentially whether that converts fast or not. There is a lot of that's a luck.
Training.
Yeah, and imagine there is a problem which this is the error function going to have, suppose this kind of thing. I think that you would have started here, would have come here, would not have reached here. Gradient approach. The gradient essentially comes down.
So we need to have an optimized LR actually. We need to have an optimized LR for that.
Optimize the English, but you have to mathematically have to tell, correct?
Optimized learning.
Yeah. So that's what is the proof that what is the formula or algorithm to find out initial weight.
In case of neural networks, we have backpropagation algorithm. In case of other models, we can employ gradient descent.
No, now example in the model is as now this is fixed. Now Now sir is asking how do you compute the weight? We have to assume that weight here. From there, go there and find the weight and then compute. So this is also open problem. Even assumption of the weight also is open problem, still not solved as such. It's going on. So the companies, enterprises, all providing hardware and memory infrastructure for this problem. Okay, this is what essentially is happening. But that is, I give you kind of a rough. This MNST itself, I think 500,000 neurons are there. Weights.
Actually, most of our students here, many are electronics engineers. So they will be interested to knowing that Rosenblatt first tuned the weight using potentiometers.
Oh, okay.
Actually, manually he did that using potentiometers.
Oh.
That was in the 80s.
Really?
Not 80s, 60s.
Oh yeah, of course, that is maybe I just quickly take over this one because since the question comes here, this might be a little interesting one. See, this is an easy function for us, correct? X minus x whole squared plus 2, right? This is a good function, not like this one. What I drawn is not good. How this function going to look like? Who's going to help me now? This, see, at 6 it is 2, right? This way, suppose this one, right? Choose, right? Thank you. So this is a good function, right? This is a good function. So wherever we start, we come here. Whether we start here or there. But in this kind of network, we don't get this kind of things. A lot of research is happening. Of course, guys are what they're doing, they're bounding by projective geometry. What they're doing is they're bounding this curve. This curve, no? This curve itself they're bounding like this. Correct? That itself have various variants and so and so. Then it becomes this problem. This problem is solvable problem. This problem if you go through it, you can easily see it, right? Of course, this is until a tensor flow. See, if you ask the devices also, you can put that place. This is our popular method, correct? Save, sir. Here also we use save. The new weight equal to old weight plus alpha times of the gradient, correct? This is what essentially we run on it. The same logic for here also. But only the numbers are too many states, not a one way. And so only x is one, so it's, analytically we can do. As a human being, we cannot do it with
facial recognition, how many layers
Oh, I'll count that. I'll just count that. So now you have a kind of a thing, finally it should have converged to C of 5.99, correct? Instead of 6, it converged kind of thing. So, okay, now.
So you had a general equation in the form of x and k with the learning rate alpha.
Yeah.
So what was k over there?
K is a state. I am studying k. Previous for me is k minus 1. The next step will be time k plus 1. So that to know about k, to compute the k, I need to know k minus 1 plus the tangent of this.
Actually, the iteration count is k.
Okay, you can call it iteration count. It's not an iteration, it's any time given function. But I started here, the next might be get right. If alpha is smaller, you will have so many iterations. Your question.
No, how many layers?
Okay, sir, again. Okay, then maybe I should take that one to answer your question. Just give me 1 minute. Sir, this is essentially kind of research, people are agree on that. Based what is the kind of accuracy which we see from the human being and the machines. Suppose this is what I say, this is a computer. If I say 100% we agree, but the computer says classification we don't agree to 90%. So there is a kind of dispute in that, whether everything is ready to accept or not. But now we have interesting data on that. If you look at that, the first level is 28%. And the human is 5%. This is 5, right? 5. So this is what we essentially agree, but now machines can produce much better than our eyesight. Machines can produce much better than our eyesight. Okay, so now,
what is this percentage?
This is the probability of error. Probability of error. So the wire girl in assembly line, it's assume that this is coming out of the production line. I know they tend to do five mistakes actually. Even though they seeing it, there is a mistake happened. That's the way the quality control department is very active, right? Otherwise, no work for quality control department as such. So that is the error happening in human being also. In fact, that error is potential in healthcare. That's maybe I should motivate that example right now. Now, since we are there at the place now. Maybe Kailash will finish it and then go, or we'll do the parallel. That's the beauty of this. On this demand, I'll take this example now, the human. Sir, I have all these things that I can share with you. So the problem is, the cognitive computing can do much better than our eye. Right? That's the question. But there was a nice example which I had here. I'll run through this for you. Of course, this has been used primarily in the many upcoming machine industry where 4 points, and the human the contestants keep us alive in this problem to solve. Okay. So what we have done with this problem, we have done with this accuracy. What we have done is the classification problem. Means classification problem we have done with it, we have almost agree. What machine is done correct kind of thing. And also object detection. Here also we are almost agree that yes, object detection is good, but machine is doing much better than. So we are doing little intermediate than that. To do that such kind of thing, every neural network. This network has something like a 5 lakh smaller. It starts with 2.3 million, 0.5 million to 2.3 million. It goes more like a number of transistors. This other going maybe, ma'am, morning was asking. The weight also going quite. It's like the number of transistors goes into the chip. The number of the weights also
more than billion transistors.
But these are all millions now. Maybe down the line, another 5 of these kids might be running with 10 billion weights. Now all the modern systems we are running in the millions. That's the question. In terms of order of millions, 2, 3, 4, for classification. But maybe things have become tougher. Maybe that's why morning I was asking. Things become tougher for this problem. Object tracking. Because what happens is, this is a problem which in the industry 4.0, very static environment. And the thing is moving, whether it is correct, this is tested or not, the buyer has to classify, then goes for a production acceptance. This is all like, kind of static well done. But this is also more or less static, so little bit of the counting and everything goes on. But it's more of dynamic. We want to track that. For a car, this is very useful. This is what useful. Now we're doing it right. ADAS, Advanced Driver Assistance System,
driverless car.
Oh, that's a little higher one. Even level, okay, driverless car is a 5 level, right? Of the ADAS 1, 2, 3, 4, level 5. So now cars are coming in America. Most of them might be operated. The ADAS level 1 is popular now. It's a parking also helps us automatically for radar. Which actually I work. Presently my work on radar is passing through. I have 60 grants and that's what my regular work actually I'll show you. So these are the done problem. Problem is become here is very intensive. Object tracking. there is no research that is this many layers required, this many weights required, what could be put. Lots are happening in that tracking. But most essential is semantic segmentation. We want to know where the boys are heading towards. Why he is heading. It's not like, we are asking like, meaning out of their, walking. Why he is walking there. If you know a car knows why he is walking there, the car can take a decision of crossing that boy or not. So the semantic questions, what is the purpose, whether the boy coming and throwing the stone or he is walking away. This is, but camera can only tell us whether the boy crossing or not.
Do you have any results for the semantic segmentation?
I'll just count there. There are 5 problems like that. That's what I'm wanting. I was telling RNN based one. So a lot of things are coming from the text based one. Okay. So given a 1-page thing, if you want to condense within 5 lines.
Yeah, so you have some results.
And something it is happening around.
Oh, okay.
So that mathematical calculation also put down. So the most another distance segmentation. That's a combination of tracking and.
Have you used the YOLO algorithm in any case over here?
What
YOLO algorithm.
Huh?
YOLO.
Oh, okay. See, there are a lot of models are evolving now. Every research is putting now things are happening too good out here. It's like, but here are more or less matured one. It's like, competitive, whether I can do how many objects I can classify, 10 or 20 per second. That's the kind of selling. IBM might say I can classify 100 objects per minute. Someone might.
So what model did you deploy to find out the image segmentation? To predict which side the boy will cross on a real estate?
That's a research problem. That's what it's open research problem. Why is this boy running? So question is, we are not questioning about the boy running or not. That is here. Object tracking, this is that. We know that boy running here. But the question is why he is running. There's a next level of questions. That's not only one sensor. So what I'm trying to figure out is, by using only one sensor, we cannot have hypothesis for that one. Our hypothesis is bounded to only one, this one. We have to go up. So this I told you about acceptance. So we'll have one case study here, simple quick case study, but it's interesting one. This is really enlightened me quite a bit to go through this much more. So what happens is, we all look at the sky, right, when you walk out, or, of course, if you have Calcutta, you may not die everywhere light for you. Like village case, like we see when you go. So in Bangalore also a little drive by 10-15 minutes, you'll get this kind of scenario. It's not very big like this. So look at the sky. Can you make out anything as a normal human being? Extremely difficult to make and count. Maybe some people will have a very good, parents given a nice neuron for their visions, they might be able to find, like someone can hear very well, someone may not be able to hear well, correct? How does computer compete as a window over us? This example just see. Imagine if I would have given this someone, normal human being, they would have computed 308. It says there are 308 stars are there in this. But there is no way we can prove at this truth. There is a story now that Krishna Deva Raya kingdom. There is a one gentleman, what is his name? Tenali Ramakrishna. In Tenali Ramakrishna, the contest was very interesting. So people tend to make fun out after one other time. So they're doing some things and I sometimes we say that they don't. So what happened is the question is how many crores are there in this kingdom? How do you solve the question? So he put out a number, immediately gone out and then immediately put out the number. So the people are a bit worried and they went and counted as much as possible. I came out with a different number. Then they told the Raya government, see whatever the number is told, it's not correct, it is something. I said exactly, when they put out the number, when it went to account, many of them went away. She is super intelligent, right? He used this algorithm to define that way. So when that kind of escapism we cannot do it because the given picture as this is. How we are going to overcome that problem. So then we need a help from image processing people who understand image signal processing, image everything. So bring them back here and then deploy here. So you can see some kind of normalization, some kind of filtering, this concept. This also is not very good for us, Even with this also, normal human being eyes cannot see. There's a lot of errors can come, problems can come worse. I'll tell you the application at the end. But let's look at the start now. Start on. So this is a kind of a okay. And now we see, right? This is the Laplace Gaussian filter. And this is very interesting because you see to the Laplacian gives the kind of edge and finding the edges. The Gaussian gives more of a smoothing. So make them most of them friendly. And then bring them to kind of filtering. So that's going to give you some kind of guidelines for 3x3 or something else. Now we see here. See, this is the filter now. In the filter also we see how human being we derive some value. The lot of weights are here, rest are zeros and here, right? So then we can make sure that why do you multiply all things? Why not have this first code? So how intelligently we need to come out here? This kind of physical meaning only going to give us, not by closing eyes and put 3x3. So we took it and by us. Way of filtering finding out the filter for this one. So we went through quite a bit. Then we saw we are seeing that the weights more are in the this output, other place not adding too much value in it. So we don't gain too much, even go bigger and bigger. That's what it means. So every algorithm come to arrive this kind of conclusion rather than blindfolded 3x3 or 4x2. That's my answer. So I went through that instead of just assuming one number, I went through the bigger one. That things to quite comes out. Now you see, then now as a human being,
we will restrict it within 5 minutes.
No, it's almost done. So we have this, right? So now as a human being, we can see very nicely. The same picture what we did with the image processing magic which not magic, building. We come out right. So then if we go and count, it's giving a result 289, correct? It's giving a 289. But we don't know whether it's true or false. We'll prove that whether this is correct. How we are going to prove that was? Yeah. So rather circle along the one wherever we identified. Imagine there was a 1 here. We did not identify, then that circle problem, correct? So that's the way we identified 289 of the filtering is fine. So this is essentially kind of moral of the story. This is what the circle they talked about. But where the application in this is healthcare, in particular, the early morning it goes to diagnosis centers like Cloud9, all this, everywhere 100 or 70 people do the blood and they want a result within 10 o'clock or 5 o'clock, 4 o'clock. I'm sure you also see, morning you give blood, they'll ask us come evening, right? 5 o'clock. Sometimes next day also, based on the load. So that's because when the give this blood samples to the counting people, they have their own limited how many they can process per hour. So they only count how many things there are in the microscope and then they give the result. Sometimes the results might be good or not good, the 5% error carries. But now with this advent of this one, we can make the machines to work. We can make the machines to work, but our advantage, what we really look for it. Yeah. What we look for it. So this is essentially going to give us the healthcare advantage of this place, because the machinery, the classification is now presently an object detection and classification. These two ones. I'm not talking about the third one. Object detection and classification, it does much better than the human being. So it's safe for healthcare diagnostic centers. to put this one to run in the kind of application which maybe I just show the picture about and then going to run a full. I just ran this one. And the open problems are there. It's for youngsters and challenges also. The what happens is this, I took a real blood sample, so like that. Then kind of count this one. But this is not having only one star. We identified everything as a one. Here it's not a one. These items are very different. There are items are the black ones are kind of parasites, which is the liquid when they put their stuff there. There are the others. These are the items. And moreover, the length of these strings, other people are wanted it, essentially. So the 4 items are there. 4 items need to be classified, basically detect and then counted out. The 4 count comes, then we are meaningful. Of course, this is problem. I just touched it. This is what essentially going to be helpful for us easily. Imagine we have the X system, which I told. So we have, and that X system goes in every healthcare place, diagnosis center. They can even manage 1,000 people per day within half an hour. Within half an hour, even 20 minutes taking. The moment they finish it, before even they pay the money, results can come out on their mobile phone as a diagnostic test. So we can cut short that one day gap presently with this kind of thing without going through formal like health company like Philips and GE and so on and so forth will come in that. Of course, government also needs to play certain role here because they talk about what is it called? Because health means there's a lot of standards and so on and so forth. This is the place things can come. A lot of places happening. With the shortage of time, I'll stop here, but although there are questions and things, I'll have to keep in touch with you all. So I'm happy to see, Calcutta. Of course, we keep Calcutta is high. When in fact there was a kind of thing when I was a student in IIT Bombay, Professor Sena was a guest. So I was.
So do you have any GitHub profile or something like that of your own?
A GitHub, I have it. I don't put too much, but I share with you. No problem. I'll share with you. So one day we had a guest lecturer from Professor Sena Rao, and he was starting car and told you. So Sena was speaking very much Professor Nath. Our director was Professor Nath then. He was tall and gigantic gentleman. He caught up and told, I'm telling this professor to go to Calcutta to accelerate the process of getting Nobel Prize. Of course, we are all lost and we didn't class as their whole life, So this city was known for high quality scientific research and things. I'm so happy I told my friends that tomorrow I'm going to Calcutta, maybe I have to go, it's very nice. So it's nice to interact with all the people, youngsters and also professors asking a lot of intelligent questions. So I'm very happy to share whatever limited knowledge I have in this section. Thank you.
The first workshop in Calcutta, and let us know. Do join our virtual university, and also I'm asking your principal to be part of the OpenPOWER Foundation, and he also agreed to it. And I'm hoping that you guys enjoy the lab session and then connect with us for further access of systems, and definitely we will provide you a chunk of access also as part of this collaboration. Okay? Any other questions? Anything you want to do or anything you want to share as part of today's workshop?